Welcome to this new MOOC, an intuitive introduction to probability from the University of Zurich and Coursera. My name is Karl Schmedders. I'm your instructor in this class. I'm a professor of quantitative business administration at the University of Zurich. I'm very passionate about business analytics, probability, statistics, optimization, you name it. And I really want to get you excited about probabilistic thinking in this MOOC. I hate probability. You won't believe how often I've heard those words from my students in the past. And maybe you have said it too, maybe you have thought it. Or a buddy of yours has said the same to you. And interestingly, if you Google "I hate probability", you will be surprised by the number of hits you find and the number of blogs on this particular topic. Now, all of us have had bad experience in probabilistic or statistical classes. Some students really gave me great quotes over the years. There was one woman who once taught me, "Karl, probabilistic thinking is the opposite of common sense. I leave my common sense outside the classroom before I come to your lecture." Another student said, "I don't need probability. I have a good gut feeling to make decisions." So, I know many of us have thought this or have heard these kind of opinions. And I understand that given the way we often teach probability, that people can think of this or can think of probability this way. Now, instead, I really want you to get excited about probabilistic thinking, and I want to show you many cool applications of probability and other applications of probability in everyday life. Let's think about this. How often do you see probabilities in your life? This morning, I checked the weather forecast, and it said today there's a 40% chance of rain here in Zurich in Switzerland. 40%. There was already my first probability. How should I think about it? Should I trust that probability? How should I react on this probability? Last year, I had a surgery, and afterwards my surgeon told me, "Karl, as a result of your condition, your probability of getting cancer is tenfold. But don't worry, it's still small." How should I feel about this? How should this affect my lifestyle? How large is 10 times larger than for the rest of you? Another very important question that essentially goes back to probability. This past summer, 2016, there was an infamous Brexit vote in the United Kingdom. In the weeks leading up to the vote, you read the newspapers. Oh, the Brexit is becoming more likely. Oh, it's less likely. Oh, the stock market thinks the probability is this much. Or the opinion poll says the probability of a Brexit is shrinking. Another very important public policy issue where probabilities were talked about over and over in the weeks running up to the vote. Those of you who have flown in the past or have been on airplanes, you may have noticed that the airlines overbook their flights. They sell 400 tickets even though there are only 300 seats on an airplane. Why are they doing it? I will explain to you how simple probabilistic thinking is behind the airline's behavior. Those of you who invest money in the stock or bond market or in new ventures may have thought about how risky is this investment. Again, that's a probabilistic concept, the riskiness or volatility. And we will talk about metrics that describe this. Many of us every day get advertisements. Oh, people like you who bought this book now also buy this other book. You should buy it too. Why are they sending you this particular advertisement? Again, it goes back to probability. And we will talk about this. Even in the court, we all have heard in movies, beyond any reasonable level of doubt. What is that? Another probabilistic statement. And I will show you some interesting, thought-provoking examples of using probability in the courts. So we really see that probability is everywhere in our daily lives. Now, if you decide to take this class, I have a favor to ask from you. Have an open mind. I realize many of us, me included, had very frustrating experiences with probability in the past. Give me a chance to get you excited and to show you my enthusiasm about probability. So please have an open mind. My TA Jose and I will show you various little examples, some in Excel where we actually calculate some probabilities. Try to reenact those on your own computer so that by learning by doing, perhaps you also develop a better intuition for probability and have some fun playing with these numbers. So that's important to me as well. Try to have some fun. And finally, contact us with questions, enter the forum. There are many people here who want to help you, Jose and me included, and so that we have a fun and thoughtful experience here in this new MOOC. Thank you. And I was look forward to seeing you in lesson 1 of module 1. Welcome to lesson 1 of module 1 of an intuitive introduction to probability. So, we want to talk about probabilities. Before we get into formulas and calculations, it's really worthwhile to think about what is a probability and how do we define probability. Interestingly, there's not just one definition of probability. There are 3 widely accepted definitions of probability. And so, before we look at some slides and examples, let's talk about the 3 definitions. The first definition, called the classical probability, or also the definition of exact probability, is objective probability, is the one that we use when we play games with cards or with dice, or if you go to the casino. Here we see I have 4 options. If I choose a card, we see there are 3 black cards and then there's the ace of hearts. And now if I ask you what's the question if I shuffle those cards and pull a card, what's the probability this is the ace of hearts? I think you and I can agree on it. It's 1 in 4, 25% probability. Objective, I think there's very little discussion, unless you think I'm cheating. There's very little discussion and we can quickly agree on the probability. This particular definition is very limited. It's very simple, intuitive. Maybe that's what you saw in high school, in college, or in other classes. And we like it because it's so easy, but frankly, in everyday decision making, it's utterly useless. The reason is it's very limited. It requires that all outcomes, like in these cards, all 4 cards are equally likely and we can easily agree on the probabilities. Often that's not the case. And therefore we need 2 more definitions of probability, which both actually turn out to be way more useful in everyday decision making. So let's talk about the second definition. It's called the empirical definition of probability, also the definition according to relative frequencies. What's that? In those situations, we look at past data. For example, before a pharmaceutical company can bring a new drug to market, it has to do a lot of tests. The idea behind these tests is now to assess the probability that this new drug will help a patient with a particular condition. We also want to assess the probability that there will be side effects. So what does a pharmaceutical company do? It gives the drug in some test to patients, and then it checks out, do the patients feel better? Do we have side effects? And based on this data, it then determines probabilities, empirical frequencies that it has seen in the past in the trials to assess the probability of side effects. Similarly, when we look at stock market data, past data, to say something about the future performance of a particular investment, then we also essentially talk about the relative frequency definition. We look at past data, and from those past data points we derive assessments for the probabilities. That's the second definition. Again, the empirical probability definition or relative frequency definition. But even that definition is not always helpful. What do you do when there is no past data, when you're in an utterly new situation? For example, when Apple came out with the iPad, they didn't have past data on iPad sales. This was a brand new product that hadn't existed before. So the company couldn't look at past data. And it wasn't just a 1 in 4 chance, because it was unclear what could happen in the market. At this point, they needed the third definition, the subjective probability definition. The company had to assess the likelihood of success, the likelihood of failure, and based on that make the decision whether to bring the product to market or not. And that's the third definition that occasionally we have to use. Based on perhaps my gut feeling or my life experience, I assess uncertain situation without data and without the easy counting that I can do with cards. To summarize, the key takeaways of this first lesson. There are 3 very different definitions of probability. The first one, the easiest one, the exact definition that we use when we play cards. Second, if we have lots of data available and we think this past data is relevant for a probabilistic assessment, we use the relative frequency definition. And finally, the third definition, if I don't even have data, the subjective probability definition. In the next lesson, we will define these 3 concepts more precisely using some mathematical language. Thank you, and please come back to the next class. Welcome back to Intuitive Introduction to Probability. In the last lecture, I gave you some intuitive definitions of how we can define probabilities. There was a classical definition, the empirical probability definition, and the subjective probability definition. In this lecture, I now want to be a little more precise and give correct definitions of what a probability exactly is. And we will return to those 3 definitions. So, we need a little language to describe the probability setting. There's first a random experiment. Sounds kind of strange, sounds like we're in a lab, but in probability theory, anything that has an uncertain outcome is called a random experiment. That could be rolling a die, that could be pulling a card, this is a roulette table, but it's also in the real world. The weather next Monday, or if you think about the stock price of your favorite company, the stock price next Tuesday. We don't know those are uncertain outcomes, and therefore in our language, those are random experiments. Now, what can happen in a random experiment? Those are called basic outcomes. In a die, it's very easy. 1, 2, 3, 4, 5, 6 are the basic outcomes. If you think about the exact weather or the exact stock price, this is already a little bit more tricky, and we will see examples as we go along. The collection of all basic outcomes are called the sample space. And I apologize, we need a little notation. Here's our first notation in this class, S for the sample space. Now, when we want to define probabilities, we need subsets, some elements, perhaps not all of them, of a sample space. And those are called an event. And again, we need a little notation. Those are typically denoted by capital letters, A, B, C, and so on. Now, having said this, we can define probability. That's the chance or the likelihood that an uncertain event will occur. That's a number that's between 0 and 1. Some people prefer to use percentages, 0% to 100%. Now here be careful. A probability cannot be larger than 100%, cannot be 120%. It can also not be negative, minus 10%. Sometimes people confuse growth rates, which can be negative or larger than 100%, with probabilities. So please be careful. Probabilities are numbers between 0 and 1, 0% and 100%. And now we can give precise definitions for the three probability concepts. The classical probability concept rests on an important assumption. All basic outcomes are equally likely. So, for example, in a fair die, that's given. Every number 1, 2, 3, 4, 5, 6 is equally likely. And then the probability of an event is the number of elements in your event divided by the total number of basic outcomes in the sample space. We'll see examples soon. Now, as I say here, in addition to fair die, that is true in a lottery, at a roulette table, and so on. Now, this key assumption that all the basic outcomes have to be equally likely is often not satisfied when we talk about real-world applications. And therefore, this beautiful definition, while helpful when you play a card game with your buddies or a dice game with some kids, is essentially useless for real-world applications. That's why we need more definitions. If you have data and you can derive proportions from historical data, that's when we get to the empirical probability definition, also called the relative frequency probability. Here the idea is now that we have repeated trials of an experiment. For example, I may look at the weather on a particular day for the last 20 years and say, oh, can I use some average there to make a prediction? What's the probability it will rain? What's the probability it will be sunny? Or if I think of stock prices in the stock market, people in finance love to look at the last 250 trading days and say, how many days did the stock go up? How many days did it go down? And based on that, get empirical definitions. So the definition says, how often did an event occur in a series of trials divided by the number of trials. And that's now the empirical probability definition, also used in medicine, in the pharmaceutical industry, whenever we do drug testing. Sometimes things get even worse. You don't have data, you have no clue, and at that point we go to the subjective probability definition. Very important, for example, if you have a new product development, you bring out a brand new product, a really disruptive innovation. You have no idea whether your customers like it or not. Maybe you have some, what managers like to call gut feeling or experience. And based on that experience, you say, oh, I think there's a 75% chance this will be a successful product. And so in that case, we talk about subjective probabilities. Very important in managerial decision making and everyday decision making. Now, basic probabilities have to satisfy some rules. Now, I have to give you 3 rules. Looks a little mathematical. There's nothing to be understood here. These are also called axioms. Or, after a Russian mathematician who was the first to write these down in 1933, also called Kolmogorov's axioms. These are just assumptions that we put in place for probability theory. Everything else can be derived from this. Rule number 1. The probability of any outcome in the sample space, P of S, must be 1. Something must happen when we do our random experiment. P of S is 1. Second rule, very intuitive. Any probability is a number between 0 and 1. Can't be larger than 1, cannot be negative. Please keep that in mind. And finally, the first, a little more complicated rule. If you have 2 events that have no elements in common, also called disjoint by mathematicians, then the probability that A or B happens, or the probability that A union B happens, equals the sum of the individual probabilities, P of A plus B of B. If that looks a little tricky already to you, let's look at an example, and let's go back to fair die. What's a random experiment? I'm rolling a fair die. I don't know what's going to happen. That's now my experiment. What are the possible outcomes? 1, 2, 3, 4, 5, 6, and they together build the sample space. Now I told you about events. Events are subsets of S, and here I picked an event A, the even numbers, 2, 4, 6, and the event B, 1 and 5. And now let's look at A and B and their probabilities and see how this works. What's the appropriate definition here? I don't have to make up probabilities. There's no subjective probability here. I don't have to roll the die 1,000 times to determine empirical probabilities. Since we believe it's a fair die, we can use a classical definition. All 6 numbers are equally likely, and so I'm allowed to just divide. So clearly P of S, P of any number 1 through 6, is equal to 1. A 7 cannot happen, a 0 cannot happen, pi cannot happen. Now let's look at the probabilities of the two events. A has 3 elements, 2, 4, 6. 3 out of 6 is a half, 0.5, 50%. B only has 2 elements. So probability of B, 2 divided by 6, 1/3. So here we used the first definition, classical probability. Now A union B. Hopefully you remember from your middle school math classes, if I have 2 sets and I build the union, I take all the elements together. So if I take A, 2, 4, 6 with the union of 1 and 5, I get 1, 2, 4, 5, 6. Probability now of A union B, of either A happening or B, is 5 divided by 6. 5 elements divided by 6. Notice that those two events have no elements in common. There's no number that's in A and in B. So they are disjoint. The intersection is the empty set. And therefore now I can use my probability rule. The probability of A union B is the sum of P of A and P of B. 3, 6 plus 2, 6 is 5, 6. And guess what? That's exactly the right answer that we saw before. Those are now I showed you now the 3 axioms, the fundamental rules. From those we can derive further rules, some additional rules that are very, very helpful. First, the complement rule. What's the complement of a set? The complement of an event A or the set A are all the elements in S that are not in A. And not surprisingly, the complement rule says the probability that the opposite of A happens is just 1 minus the probability that A happens. And then we have the addition rule, the general addition rule that always holds, even when A and B are not disjoint, when there is something in the intersection. And then the rule gets a little more complicated. Then the probability of A union B is P of A plus B of B, but then now I need to subtract the probability of the intersection, because otherwise there would be some double counting. Let's look again at our little example. What's the opposite of an even number? 2, 4, 6 is the odd numbers. The complement are the odd numbers, 1, 3 and 5. The probability of an odd number is 1 minus the probability of the even numbers. 1 minus a half, bingo, is a half again. Now let's look at an event C that has the elements 1, 2, 3, 4. A union C now is 1, 2, 3, 4, 6, 5 numbers, 5 out of 6, so the probability should get 5, 6. Now if I use the rule, probability of A union B equals P of A plus P of C, and I add A is 3, 6, C has a probability of 4, 6, I get 7, 6. Oh! That's not the correct probability because I'm double counting the numbers 2 and 4, which are both in A and in C. And therefore I need to subtract them out. That's why we now have this general rule. And bingo, I get again the right answer of 5 divided by 6. To summarize this lecture, I gave you formal definitions of the 3 probability concepts that we have. Very important, familiarize yourself with them. It's not always a classical probability that we learn as kids as soon as we play a dice game or we play a card game. There are more important definitions for real-world decision making, the empirical probability definition and the subjective probability definition. I showed you the fundamental rules, also called the axioms of probability, and finally 2 derived rules which are very helpful in applications, and we will see them in action in the next couple lectures. Thanks for your attention. I look forward to seeing you back in the next lecture. Welcome back to an intuitive introduction to probability. In this lecture I want to show you a first example that's a little more complicated. Calculate the probabilities there within a spreadsheet, show you how we can easily do that. And then I want us to take a first look at the concept that's very important in probability called independence, or also sometimes statistical independence. So let's look at the sum of two dice. We now want to roll two fair dice. And I care about the sum. Those of you who like gambling may know the game of craps, and that's where this is exactly important. You want to roll two dice. So what are the possible outcomes in the sum of two dice? Yeah, 1 plus 1 is the smallest number, that's the 2, and it goes all the way to 12. 6 plus 6 is the largest sum. So the basic outcomes in that sum is 2, 3, 4, 5 all the way to 12. Together our sample space capital S. And now we can think of events. What's the probability of an 11 and a 12, or a 12, or what's the probability of a 7? Let's now move over to a spreadsheet that I've prepared for you, where we can look at the possible combinations and the probability of the sums that are possible. So here we are at our spreadsheet, where we want to look now at the sum of two dice. So here in the left table, I have in the left column the 6 possible numbers that the first die may show, and here in the top row the 6 possible numbers that the second die may show. So 6 times 6, notice here we have 36 combinations, and in the table I wrote for you the sum of the two dice. So here 1 plus 1 is a 2. Here 3 plus 1 is a 4. Now notice the different numbers show up different many times. There's only one way to obtain a 2, 1 plus 1. But for example, there are 3 ways to obtain a 4. There are also 3 ways to obtain a 10. And so this now shows that these probabilities will be different. We have 36 possible combinations. So now here on the right, I looked at the 11 possible sums, 2, 3, 4, 5, all the way to 12. And in this column called counts, I wrote down how many times does the number on the left, the sum, show up in that table. The 2 only shows up once. The 4 shows up 3 times, just like the 10. And notice now, the most common number is the 7, 6. There are 6 combinations to roll a sum of 7. 6 plus 1, 5 plus 2, blah blah blah, until 1 plus 6. Since we have 36 combinations, in the next column I calculated the probability of the 7 numbers for you. 6 out of 36. 1/6 is a probability that the sum will actually show a 7. This is a number that's most common, and those of you who like to play craps, you of course know that. 2 and 12 are the 2 least likely numbers. Only 1 in 36 chance for each of them. That's less than 3%. So we see here the numbers are different, but by counting the possible combinations and the total number of combinations, we can calculate the probabilities. This sums up the discussion of the spreadsheet now. I will now return to the slides, summarize what we just learned, and alert you of some dangers. What have we seen? The sample space has 11 elements. And here's now a popular mistake that I see a lot from my students. They think, oh, we have 11 possible numbers, so the probability of all of them is 1 divided by 11. But we just saw in the spreadsheet that's not the case. Why? Because there are several ways to get a 7, 6, 1, 5, 2, but there's only one way to get a 1, which is a 1, 1, or there's only one way to get a 12, 6 plus 6. So here's the danger that people sometimes think, oh, my sample space has that many elements, the probabilities are all 1 divided by them. That's here not correct. The assumption that all probabilities are the same, that's not correct. So how can we use that classical probability definition to obtain these probabilities? That requires us to take a different look or a different view of the problem and define the outcomes and the sample space differently. Instead of summing them up, let's first look at the pairs. First die, second die. What are now the possible outcomes? 1, 1, 1, 2, 1, 3, 4, 4, 4, 5, 4, 6, 5, 1, all the way to 6, 6. Now we see our sample space has not 11 numbers, it has actually 36 pairs. Number on the first die, number on the second die. 6 times 6, 36 combinations. And they are now all equally likely. The probability of 1, 1 is the same as a 2 on the first and a 5 on the second. And so now here I can use the classical probability definition the way we saw it in the last lecture. 1 divided by 36. Now there's a little more work to think about what's the probability of a 4. A 4 has 3 ways as a sum of occurring. First a 1, then a 3, first a 3, then a 1, or a 2, 2. So there are now 3 of these pairs that sum up to 4, 3 divided by 36, and that's exactly the probability that we previously saw in the spreadsheet when we saw those 3 combinations, 3 and 36 or 1 12th. Now let's look at a different way at calculating these probabilities. Notice the following. When the first die rolls and shows up a 1, that does not affect the second die. It's not like the first die calls up the second die and says, dude, I showed a 1, you better don't show a 1 because otherwise the dumb humans get confused. No, the probability of a 1 is still the same as it was before I rolled the first die. So that means the outcome of the first die does not affect the outcome of the second die. This is the concept of independence or statistical independence. More generally, 2 events are called independent if event A occurring or not occurring does not affect the probability of event B occurring. Why do we like this concept? Because now it's very easy for me to calculate the probability of the intersection of 2 events. Because now, if A and B are independent, the probability of A and B, A intersected with B, is just probability of A times the probability of B. And now I can use this with my 2 dice and ask what's the probability of first a 1 and then a 5. Oh, probability of a 1, 1 and 6. Probability of a 5, 1 and 6. 1 6 times 1 6 is 136. And so now I can finally show you a second way of calculating the probability of a 4. A 4 again happens if you see a first a 1, then a 3, first a 2, then another 2, first a 3, then another 1. Those 3 basic outcomes, or if you want to think of them as single outcome events, are disjoint. That means I'm allowed to add the probability of a 1, 3 plus a probability of a 2, 2 plus a probability of a 3, 1. Each of them now I can calculate via my multiplication rule. 1 6 times 1 6 for the first pair, the same for the second pair, the same for the third and last pair. So I get 1 on 36 plus 1 in 36 plus 1 divided by 36, voila, we are back to 3 divided by 36, 1/12, the number we saw in the spreadsheet. And that already brings me to the end of this lecture. What are the takeaways? In that very simple example of the sum of 2 fair dice, we already realized we have to be careful in defining the sample space. Because that later helps us or with calculating probabilities or makes calculating probabilities a little more tricky. I gave you a first look at a concept that's very important in probability, the independence of events. And I showed you a cool consequence of that concept, namely the multiplication rule for independent events. We will see this in action in future lectures, so I hope you will be back for more fun with intuitive probabilities. Thanks for your attention. Welcome back to an intuitive introduction to probability. In today's lecture, I want to talk about an example of subjective probabilities. In my experience, whenever I introduce the concept of subjective probabilities, students early on feel a little insecure about, what does it mean, subjective probabilities? How do I develop them? Can I just pick any numbers for subjective probabilities? Of course we can't. Your subjective probability cannot be 120% or minus 5%. That would violate the axioms of probability. Now let's look at an example where I would like you to develop your own subjective probability. Here's the description of a woman by the name of Linda. She's 31 years old, single, outspoken, very smart, majored in philosophy. When she was a student, she was deeply concerned with discrimination, social justice. She participated in anti-nuclear demonstrations. Now, I'm going to give you 8 options that describe Linda. And I now would like you to think about what do you think is most likely, second most likely, lowest probability. Of course, based on this description, your idea of Linda that you have in your head may be very different than the idea I have of Linda after reading this. And so now, based on this and your experience, your gut feeling, you need to develop some subjective probability. So what do you think? Do you think Linda is now a teacher in an elementary school? Or does she work in a bookstore and take yoga classes? Active in the feminist movement? Is she a psychiatric social worker? And so on and so on. When I give this question in class for my students to develop subjective probabilities, I ask them to give me numbers 1 through 8. Most likely a 1, least likely an 8. In this format I can't quite do this, so here now we do a little in-class, in-lecture quiz. I'm now going to offer you a couple solutions and pick the ranking that's closest to your subjective probability. It may not be exactly your subjective probability, but pick the one that you think is closest to your feelings. I hope you now filled out the in-class quiz and picked your favorite description. Here's now, I want to show you one answer that was among the options that you had that's very popular among my students. And that's the following. People usually rank, many do, very high that she's active in the feminist movement based on the description they got. That's usually something people rank very, very highly. Perhaps a 1, a 2 or 3. What I see with the vast majority of people who have to answer this question, they rank F, Linda as a bank teller, very, very low. So they say it's very unlikely that Linda now works for a bank based on the description. And the last option, Linda is a bank teller who's active in the feminist movement, usually gets sort of an average ranking. Now, let's think about whether this is really possible. Before we think about Linda, allow me to go back in an abstract fashion to 2 events, A and B. And here we have what's called a Venn diagram. There's a sample space, S, all the possible outcomes. There's a set on event A with some outcomes, B with some other outcomes, and A and B may have an intersection. We saw those an example of this sort in a previous lecture. Now notice the intersection of A and B. Remember from middle school math, those are the elements that are both in A and in B. This set A intersected B is smaller than A, and it's also smaller in B. It builds a subset
of A and it builds a subset of B. What this means is that it has at most as many, usually fewer elements in it than A and B. And therefore the probability of the intersection must be smaller or equal than the probability of the individual events, P of A and P of B. Let me illustrate this again with a simple example of a fair die. Look at this picture here. A fair die has 6 possible outcomes. 1, 2, 3, 4, 5, 6. A are the even numbers. 2, 4, 6. B are the first 4 numbers. 1, 2, 3, 4. The 5 is neither an A and B, but it's an S. So that's outside the 2 circles representing the events, but it's still within S. Notice now the intersection. The elements that are both in A and in B. Those are the 2 numbers, 2 and 4. And here, look at this. The intersection probability of A intersected B is 2 out of 6. That's smaller equal 3 and 6 of A. And it's also small equal 4 and 6 of B. This is a general rule. So, if this is a general rule, your subjective probabilities must obey this rule. Now let's return to Linda. Look at C, F, and H. C is Linda is active in the feminist movement. F is Linda is a bank teller. H says Linda is a bank teller who is active in the feminist movement. Ah, look at H. That's C and F simultaneously. That's the intersection. What this means is that Linda is a bank teller who is active in the feminist movement must be ranked below bank teller and must be ranked below feminist movement. Of course, your personal opinion maybe it's very likely that Linda is a bank teller. Maybe she sold out and she wanted to make a lot of money in later life. You can rank bank teller ahead of feminist, but no matter what you think, the intersection probability is going to be smaller or equal. So whatever your favorite ranking is, H must rank below F and it also must rank below C. So the subjective probabilities must have satisfy these 2 inequalities. I can tell you, I have given out hundreds and hundreds of times this questionnaire. Usually more than 80% of the students in a class get this wrong. So if you picked a wrong option before, you're in good and large company. This actually is an example of a famous fallacy, a famous way how we humans think incorrectly. It's called the conjunction fallacy. It was first documented in a series of experiments done by 2 famous psychologists, Amos Tversky and Daniel Kahneman. And here I give you a citation of a famous paper in psychology from 1983. Sadly, Amos Tversky died of cancer before he could have gotten the Nobel Prize, so Daniel Kahneman got the Nobel Prize in economics for his work, not on this fallacy and other fallacies as well, sometime later. This work is extremely influential in areas such as behavioral economics and behavioral finance. You may have heard about these fields that are now very popular, not only in academia, also in industry. And I encourage you to Google these terms, conjunction fallacy, behavioral economics, behavioral finance, to learn more about these fallacies, these mistakes that we make in decision making. To wrap up, 2 events occurring simultaneously cannot be more likely than the individual events by themselves. But often in our judgment calls we make that error. It has been well documented in many experiments. It's called the conjunction fallacy. So be careful with your subjective probability. It cannot be true that anything is possible. Obviously the probabilities are between 0 and 1, not 120%, not minus 5%. But in addition, there's also this intersection rule, the conjunction fallacy. So be careful when you develop your gut feeling and your subjective probabilities. Once again, thanks for your attention. I see you in the next lecture. Welcome back to the course An Intuitive Introduction to Probability. In the last two lectures, we first had an example of classical probabilities and then an example of subjective probabilities. I now want to complete this module with a look at empirical probabilities and a rather surprising law on empirical probabilities that we see in some areas in business and statistics and data collection. So, let's look now at empirical probabilities. Recall what that was. We look at historical data or data we collect to estimate probabilities based on observations in the real world. Let's now think about leading digits. What the heck are leading digits? If we look at numbers, the first digit in a number is called the first digit or leading digit. Here I have some simple example. 54,571. The first number, the first digit, is a 5. 182,265. First digit is a 1. And finally, is number 4. There's just 4. So the first digit is a 4. And now one can ask, let's look at data sets that we see in real life. How often do you think is the first digit of a number a 1 or a 2 or a 3 or a 9? Honestly, if you had asked me this question some years ago, I would have said, oh, they're all equally likely. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 numbers, 1/9, about 11.1% for each number. That was my naive expectation. Seemed reasonable. Here's now a really fun fact that we see in everyday data. They are unequal. In many data sets, they're quite unequal and they follow a rather surprising logarithmic pattern. Rest assured, we're not going to talk much about logarithms. But once I have to write the word log base 10 on a slide, look at this funny probability distribution. The probability of the digit d, where d is now any number 1, 2 through 9, is the logarithm of the base to the base 10 of 1 plus 1 divided by d. I only put that number on the slide to scare the living daylights out of you. You can right away forget about it and just look here at the probability distribution at the bottom of the slide. The probability of a 1 is about 30%. The probability of a 2 is about 17.6%. Notice how the probabilities decrease to under 5%. According to this probability distribution, the 9 has a probability of only 4.6%. Now here's the kicker. This law actually holds for relative frequency probabilities in a variety of data sets. It has been observed in credit card bills, in stock market prices, in the market valuation of listed companies, like in a stock index, if you think about the SMI in Switzerland, or in particular large market sets like the Russell 2000 in the United States or the Wilshire 5000. It also occurs in population data. If you look at population of cities, in districts, you find it in the size of the length of rivers or the population size in countries. There are some requirements that these data sets have. They should not have an arbitrary maximum or minimum value. So there's some basic assumptions. And the law does not apply to numbers that are assigned. So in assigned grades, in assigned phone numbers, in assigned identity numbers, it doesn't hold. Now, if you still think this is incredulous, let me show you on some real data set I recently obtained where this holds. So let's now go to Excel and I'll show you some really cool, amazing data sets. Here we are in our spreadsheet. The first data set reports US Census data from the year 2010, when the United States counted the number of people residing in its various counties. The United States is divided into 3,143 counties. Here, the first state in the alphabet is the state of Alabama, and within Alabama, the first county in the alphabet is Otago County, and it has a population of 54,571. The leading digit is a 5. The next county in Alabama, Baldwin County, has 182,265 inhabitants, so the leading digit is a 1. I wrote down the leading digits for all 3,143 counties and then counted how often does the 1 show up, how often does the 2 show up. That's here in the column count. And then I looked at the proportions. These proportions we can now think as probabilities according to the definition of empirical probability. We have here in our data 3,143 trials of a random experiment. That's how we can think of this. In 953 of them, the leading digit is a 1. 953 divided by 3,143 gives us 30.3%. And look at that. The data says 30.3%. Benford's law, in theory, would say 30.1%. Very close. Look at the 2. Shows up a little more often, almost 19%, not quite 17.6%. But in general, Benford's law is very close to our data. And look, a 9 only happens in less than 5% of the cases. So here we see this amazing law where intuitively I would have said 1, 2, 3, 9 are all equally likely. In fact, 1 shows up by most often by quite a margin. Let me show you a second data set from the United States. This one on employment in the United States. This is data from the Bureau of Labor Statistics. The United States Bureau of Labor Statistics knows 820 different job titles. Every job title has its code, and the Bureau of Labor Statistics counts the number of people that have these titles. For example, there are 248,760 chief executives. There are 174,010 so-called marketing managers, and so on. I have here the entire data set for you, 820 job descriptions. We write down the leading digits, we count the number of leading digits, we calculate the proportions. Here we have a little bit more variation, but once again, the proportions are pretty well approximated by Benford's law. The number 1 shows up way more often than the 2, shows up more often than the 3, blah blah blah, all the way to the 9. 9 is once again in last place. So here we have another illustration of Benford's law. And now the question is, what is that good for? Let's return to the slides and I will tell you. Here we are back from those data sets. And now you may say, okay, those were cute. What is this good for? You won't believe it. Benford's law is used a lot in fraud detection, in particular in accounting fraud detection. Here I give you a reference of a fascinating paper where the author shows how one can use Benford's law to analyze large data sets of tax returns and actually see whether people cheat on their taxes or not. A big topic here in Switzerland is the automatic information exchange between Swiss tax authorities and tax authorities in the EU or the United States. People are looking for people who are cheating on their taxes by hiding money in other accounts. I have been recently told by accountants working in this area that they use Benford's law by looking at huge data sets, big data you may have heard, by looking at huge data sets and seeing whether they satisfy Benford's law. And if they don't, they suspect accounting fraud. In a related issue, some researchers have looked at government data, in particular government budget data coming out of the country of Greece in the 5 years before Greece joined the euro. And guess what? Benford's law didn't hold, even though it held in other countries and it held in Greece many years prior. The authors conclude that the government doctored its budget so that the country could join the euro. So this Benford's law, as strange as it looks to us, it holds in many data sets and it has real-world applications. How cool is that? Let me wrap up. We have seen Benford's law and it's really used in accounting to detect tax cheats and other frauds. This brings me to the end of this module. We learned about probabilities, in particular the 3 different definitions of probabilities, and we saw examples of the classical definition, subjective probabilities, and in this last lecture of an empirical distribution. Thanks, and I hope to see you again in the next module.
Hello, my name is Jose, and I'm going to be your teaching assistant during this online course. What we are going to do here together is to solve a series of 5 exercises in which you are going to be able to apply the theory that you learned with Carl in the theoretical models to a very specific question. Every module starts with a short story, a short introduction, from which we will take the information to answer very specific statistical questions. So let's start with module 1. In the movie Star Wars, there is a very famous scene where some of the characters of the movie are trying to escape with an aircraft, the Millennium Falcon, through an asteroid field. So we have Chewbacca, Han Solo, Princess Leia, and then the droid C-3PO, or R2-D2, calculates the probability that they have to survive if they escape through the asteroid field. So for you to understand it, there is an asteroid field, which has some parts filled with air, through which the aircraft can easily fly through, and some parts full of asteroids. Good. The density of this asteroid field is 90% asteroids, 10% air. There are 2 types of asteroids. There are asteroids of type A, which are small asteroids, which we can find with a probability of 30% within the whole set of asteroids. There are also asteroids of type B, which are very big asteroids, which we can obviously find with a probability of 70%. So in the asteroids field, we have 10% of air, 90% of asteroids, and then within the asteroids, we have 30% of small asteroids and 70% of big asteroids. If the aircraft crashes against one of the small asteroids, it will get damaged, but it will still be able to fly through the asteroid field. However, if the asteroid is of type B, is a big asteroid, and the Millennium Falcon crashes against it, the aircraft will be so damaged that the characters of the movie won't be able to make it. So let's start answering some questions regarding this assignment, this exercise. So we can scroll down a little bit and start answering the questions. First question is, can you identify the random experiment in this story? Well, this is actually a very simple question in which we can answer which are clear. Of course, the process leading to an uncertain outcome, which is what defines a random experiment, is flying through the asteroid field trying to avoid the asteroids. Then we can move to the second question. What is the state space of this random experiment? Well, the state space of the random experiment are either we hit on air when we go through the asteroids field, or we hit on an asteroid of type A, or we hit on an asteroid of type B. So our state space in this random experiment is either air, asteroid of type A, or asteroid of type B. Then we can move to the next, also introductory question. What's the probability of hitting only air when crossing the asteroid field? Well, since we know that the density of the asteroid field is 90% asteroids, the remaining part is only 0.1, meaning 10% of probability for the state air. So we can answer this question with a clear 10%. Now we go to a slightly more complicated question, which is, What's the probability of hitting an asteroid of type A when crossing the asteroid field? Well, we know that the probability of hitting an asteroid of any kind is 90%. Additionally, we know that 30% of the asteroids that we can hit are of type A. So if we multiply 90%, which is the probability of hitting one asteroid of any kind, by the probability of hitting an asteroid of type A, which is 30%, better said, with the probability that we find among the asteroids one asteroid of type A, which is 30%. If we multiply these two values, 0.9 times 0.3, we get 0.27, meaning 27% of hitting an asteroid of type A when we just randomly cross the asteroid's field. This leads us to a similar question, which is, what is the probability of hitting an asteroid of type B when crossing the asteroid field? Well, we have to do a very similar calculation. Probability of hitting an asteroid of any type, is 90%. Probability that the asteroid, if we hit an asteroid, is of type B is 70%. So if we multiply 0.7 by 0.9, we get 0.63, which is 63% of probability of hitting an asteroid of type B when randomly crossing the asteroid's field. Now we can scroll down a little bit further and go to the next question. What's the survival probability of the Millennium Falcon? Well, now we know that the asteroids of type A are not big enough to damage the Millennium Falcon such that it doesn't survive to a hit. So the Millennium Falcon will survive if it either hits on Earth or if it either hits on an asteroid of type A. Hence, we can multiply the probabilities of hitting on Earth, which we know and previously calculated is 10%, and the probability of hitting on an asteroid of type A, which is 27%. If we add up these two probabilities, we get to 37, which is the probability that the Millennium Falcon, which is the name of the aircraft in which the characters of the movie are flying, actually survives. We can now move to the next question, which is, what's the complement of Earth? As you have probably noticed, this is also a very simple theoretical question. Well, the complement of Earth is hitting an asteroid of any kind. It's just all the other events that are just not Earth. Last question, to wrap up a little bit, is if the laws of probability are fulfilled in these examples. Well, we can count on the three laws of probability again. First, the sum of the probabilities equals 1, which in this case is true. Probability of hitting on Earth is 10%. Probability of hitting on an asteroid of type A is 27%, and probability of hitting on an asteroid of type B is 63%, which add up equals to 1, meaning 100%. All the probabilities are between 0 and 1. Well, this is, as you know, defined in the exercise setting. And the third and last law is that the probability of any two disjoint events is the sum of their probabilities, which by definition of this setting is obviously fulfilled. I hope that you have enjoyed the first exercise and that you are now more familiar when working with some data and some probabilities. Enjoy and see you in the next module. Thank you very much.
Welcome to our next module of an intuitive introduction to probability. This model concerns conditional probabilities. In my experience with students, that's usually a topic where people are really struggling to wrap their head around the formulas. So before we look at any formulas, let's look at some data, some empirical probabilities, and develop some intuition. I put together a data set here with some population data from Switzerland. Before we look at the data, let's think of the following. You come for a vacation visit to Switzerland and you meet your first Swiss person. And here's questions. What is the probability that this first Swiss person you meet is younger than 20 years old? So he or she is somewhere between 0 and 19. And then you may ask, what is the probability that this person's main or first mother tongue language is French? So we have data on this, which I can show you in a moment. You talk to the person and the person tells you, actually, I'm residing in the canton of Zurich. Question, does this information reveal anything about the answers to the previous questions? Based on this assumption, should you change your idea of this person and the probability of him or her being younger than 20 or having as the mother tongue French. Quick, for those of you who don't know much about Switzerland, Switzerland is divided essentially in 4 regions when it comes to languages. The largest part in Switzerland, people there, or the majority of the people residing there, have German as their first language. The second largest region is then the French-speaking region, predominantly in the southwest of Switzerland. Then there's a canton of Ticino, where the mother tongue for most people is Italian. Many people are aware of these 3 languages, but then in the country, in the canton of Graubünden, there are some regions where there's a 4th language, the main language, Romanche. And so we are now talking about the canton of Zurich. Here's now the Swiss population data. So the person residing in Switzerland, 20.2% of them are between 0 and 19 years old. 22.4% of them have French as a first language. So this is our data. Now, if we use the empirical probability definition, we would say you pick a random person out of Switzerland, the first language, French, 22.4% is a probability, or 0.224. Now the person tells you that he or she is residing in Zurich. Now the data tells us, wait a minute, the probability that French is the first language now is suddenly 3.2%. What just happened? You received information from the person, I'm residing in the canton of Zurich, and now you need to adapt or you need to change the probability. Before, your probability of French was 22.4%, now you lower it to 3.2%. So, this probability changed. The occurrence of an event, the person is residing in the canton of Zurich, made you change the probability. You now have a different assessment of the likelihood of the event French. Here's now the general idea, leaving the example behind us, thinking of the general concept of a conditional probability. You have an initial probability of an event P of A. That can be, again, a classical probability, an empirical probability, as we just saw in our data example, or subjective probability. Then an event occurs, an event B occurs, and as a result of B occurring, you now say, oh, I need to change my probability. I update it under the condition B, the probability is now different. Here now, we need again a little bit of terminology. At the bottom of the slide here, the probability of A, then this vertical line B, we say the conditional probability of A given B. And that's the new probability here. So back now to our example. Your original probability P of French was 22.4%. Now the event person from canton of Zurich occurs, and now the probability of French under the condition the person is from Zurich, or said more in the language of conditional probability, the probability of French given Zurich is 3.2%. And that's now a conditional probability. Now here I've shown you where the canton of Zurich is. It's in the area of Switzerland where German is a predominant language, but within this canton, 3.2% of the people speak French as a first language, while in the entire country, thanks to the large French part in the southwest, it's 22.4%. Now, let me try again to get the intuition across. In the our general setup of probability. Here you see once again a Venn diagram. We have the entire sample space of possible outcomes S. We have an event A and an event B, and then the intersection A intersect B. Now the event B happens. How should you think of this? What you should now think that S is out of the window. We no longer think of the sample space of S. Now I know B occurred, so essentially this event B is like my new sample space. Back to our example. Originally we were talking about all of Switzerland. Now, after the person tells you I'm from Zurich, our new sample space are just the people residing in the canton of Zurich. So from Switzerland we went to Zurich. Here now, in general, from the sample space S, we go to just the event B. And that's now our new sample space. And so, the outcomes outside B are no longer possible, and we can think of the B as our new state space. And then the question is, now if this is our new state space B, how likely is the event A within B? That's the conditional probability. Probability of A given B is exactly the answer to that question. How likely is the event A within the new state space B? And that's it. That's the key intuition of conditional probability. To sum up, the occurrence of some events or some information that you are given may update or may lead you to change the probabilities that you have of some events. And how we do this, or the concept of this, is conditional probability. This sums up our first intuitive look at what a conditional probability is. In the next lecture, we will now formalize this intuition a little bit more with some precise definitions. So please come back to the next lecture. Thank you very much. Welcome back to an intuitive introduction to probability. Currently, we are talking about conditional probabilities. In the last lecture, I tried to give you a first intuitive look at what conditional probabilities are. In this lecture, I now want to be a little more precise and define the give you the exact definition of a conditional probability. So, as we had seen last time, once an event B has occurred, we can think of the state space S shrinking down to B. All the outcomes outside B no longer play a role. They didn't occur. We know B has occurred. So now we want to focus on B and think, what can we now say about this other event A? Before we had probability of A on the entire state space S. What is left of that now on just B? And this gives us now the definition of a conditional probability. The probability of A given B is what is left of A in B. It's the intersection of A and B. In this case, the probability of A intersected B, and we're dividing this intersection probability by the probability of the event B. In some sense, you can think of this, we are normalizing our probabilities on the new state space B, the event that occurred. If that sounds abstract to you, let's look at our standard basic example, a fair die. We have first the event A, an even number, 2, 4, 6, x and t. Before we receive any more information, A, an even number, has a probability of a half, 50%. The event B are the smaller half of the numbers, the 1, 2, 3, also has a probability of a half. Now, I roll a die and the event B occurs. What now happens to the probability of A? That's now a question for you. Do you think with this information that B happened, 1, 2, 3, does the probability of A happening go up, stay the same, or decrease? Here we do a brief in-class quiz. Please answer this, and then it's back to me. Thank you. Okay, thanks for answering the quiz question. Let's now see what happened. So, the die shows a 1, 2, or 3. What does that mean? If it's a 1, A did not occur. If it's a 3, A did not occur. But if it's a 2, 2 is an element of A, then A indeed occurs. So, let's look at the diagram. Instead of the large sample space S, we can forget about this now, we are down to just B. B has now 3 elements, 1, 2, 3. So we see a 2 out of those 3, the probability should be a third. In 2 cases, 1 and 3, A doesn't occur. In the last case 2, A occurs, 1 out of 3. So the probability of A now is decreasing from a half, 50%, to a third, 33.33%. Let's look what the definition of a conditional probability tells us. It tells us to do the probability of A intersect B divided by the probability of B. These are the original probabilities. The intersection probability is 1 in 6, that's just the element of a 2. Probability of B was a half, 1/6 divided by a half is 2/6 or 1/3. And indeed, this definition gives us the correct probability that we intuitively would calculate looking at the picture of just B. To summarize, your original probability ex ante was a half. An even number has a probability of a half. Then you're given the information, the event B occurred. I rolled a die and I tell you B occurred, it's a 1, 2 or 3. Now you update the probability using the conditional probability definition and you realize the probability decreased and so the likelihood is now down to 1/3. Now let me remind you on a concept from a previous module, the concept of independence and dependence. Notice the information of B now changed the probability of A. So the event A, the likelihood of this event, depends on B occurring or not. That now means A and B are dependent. Now let's look at a slight change of the problem. Here now we again have the set A, the even numbers. But instead of B, now we're looking at the set B prime, which are the smallest 4 numbers. So we change B from B to B prime by adding the 4 to that event. Again, I roll a die, you can't see it, and I tell you, listen, B prime occurred. Now we go from the set S down to the event B prime. What happens now? In B prime, we have 4 numbers. 1 and 3 means A does not occur. 2 and 4 means A also occurs. So now the probability of A given B prime, you do the math, is again 1/2. So what happened? Before you said an even number had a probability of a half. B prime occurs and the probability hasn't changed. Nothing changed. You're not updating the probability, or if you're updating, nothing changes, it's still a half. Does this remind you of the concept of independence from the previous module? Now, B occurring does not make you change the probability of A. In that sense, A and B prime are independent. Let's summarize what we have seen here. I've given you a proper definition of conditional probability. Probability of A given B equals the probability of the intersection of A and B divided by the probability of B. We have seen when A and B are dependent, then the conditional probability is different from the original probability. In the case that A and B are independent, then the probabilities are the same. So the probability of A equals the probability of A given B. We will take another look at these concepts in the next few lectures. Thank you and please come back. Welcome back to an intuitive introduction to probability theory. Today, in the third lecture on conditional probabilities, I want to tell you about the multiplication rules in probability. When can we multiply probabilities, and what does that mean, and where do we have to be careful? So, the conditional probability definition that we saw in previous lecture, probability of A given B is equal to the intersection probability divided by the probability of B. If you want to think of the probability of B given A, it's the intersection probability divided by P of A. Now, if you do a little algebra and you multiply on both sides of this equation with the denominator, so in the first equation, for example, with P of B, we get this multiplication rule that the intersection probability of A and B equals the conditional probability of A given B times the probability of B. You look at this math and you say, oh, this looks kind of abstract. Actually, I'm sure you have used it, perhaps without knowing it. We use this rule actually all the time. So let me try to convince you that this is actually rather intuitive. Please recall this spreadsheet on Swiss population data that we have. If you look at the size of the canton of Zurich and the population of Switzerland, you will notice that 17.6% of all Swiss residents live actually in the canton of Zurich. And also in that data set, you will see 19.6% of all Zurich residents are under 20. They're between 0 and 19 years old. And here's a question for you. What proportion of Swiss residents live both in the canton of Zurich and are under 20 years old? So look at the numbers. If I tell you 17.6% live in Zurich, and from those people 19.6% are young, oh, what would you do? You would say, yeah, 0.176 times 0.196, that's now the fraction of people that have both. They are both young and live in the canton of Zurich. You do this and you get 3.45%. We have done this, I'm sure, in our lives a lot. If I give you half a cake, and of that cake I cut it in 5 pieces, and then I give you a piece, how much of the total cake did you get? Oh, we started out with half. I gave you 1/5, 20% of that. You would say 0.2 times 0.5 is 0.1. I just gave you 10% of the cake. So we multiply these probabilities all the time, just as in this example or in the cake example. But now let's take a look at just this everyday calculation in the context of conditional probabilities. If we take these proportions as our definition of probability, the empirical probability concept number 2 from what we saw in the previous module, then we would say the probability that someone is from Zurich is 0.176. The probability of someone being young in the canton of Zurich, the probability of 0 to 19 years given the person is from Zurich, is 0.196. And now, if we use the multiplication rule, the probability of Zurich and 0 to 19 years old is then the probability of Zurich times the conditional probability 0 to 19 years given Zurich, blah, blah, blah. You do the math, 3.45%. Exactly of what you did with your gut feeling before. So this abstract looking multiplication rule in conditional probabilities is actually an everyday concept, a proportion of a proportion. And then we multiply. Let me remind you once more of the concept of independence. Independence meant the occurrence of one event does not affect the chances of another event occurring. That was the probability of A is equal to the probability of A given B. If that's not the case, if they're unequal, we say dependence. Now, what happens if we take our multiplication rule and now assume that A and B are independent? In that case, the conditional probability of A given B is just the original probability of A. Now replace the conditional probability in that general multiplication rule and you get a specialized multiplication rule. And that's the multiplication rule I showed you in the previous module when we talked about independent events. The probability of A intersected B is equal P of A times P of B. Look, that looks much easier than the general multiplication rule. That's why people like this independent events assumption and this rule. Let's look at an example where we can easily use this. Let's say you play a dice game now with 3 dice. What's the probability of 3 ones? A 1 on the first roll, on the second roll, and on the last die. So, you want the probability of a 1 and a 1 and a 1. Rolling 3 dice, they are independent. I'm allowed to multiply the probability. 1 6 times 1 6 times 1 6 is 1 in 216. And there's nothing special about the 1 1 1. I can ask you what's the probability of first a 1, then a 3, then a 5. Same math. So you see, rather large, complex events like 3 numbers in a row, you can do this for 20 numbers in a row, for 200 numbers in a row, suddenly gets very, very easy under the assumption of independence. We can just multiply the probabilities. As simple as this is, we have to be careful in real-world applications. There often we have to ask ourselves, is that assumption reasonable? Can we really assume independence? If yes, great for you. We can use the independence multiplication rule. If, however, the answer is no, you are not allowed to use this rule. You may get into real trouble. And later on in this course, I will show you some devastating applications where people assumed independence and terrible real-world things happened. Here now, I want to give you a very simple example. Let's say you have a machine in an assembly line, and that machine carries a heavy load, and as a result, it breaks down, on average, in 1 out of 10 days. On 9 out of 10 days, it can handle the workload and it works fine. So if we use this historical data now and the equilibrium concept number 2, empirical definition, we can now say the probability of a good day is of working is 0.9, of a breakdown is 0.1. And here's now the question. What is the probability that this machine works 2 days in a row? So, if I don't know anything, I would have to say use the general multiplication rule. The probability of working well on the first day and working well on the second day is probability of working well on the first day times the conditional probability working well on the second day given it worked well on the first day. One probability I know, P of working well on the first day is 0.9. That's for my data. But what's the conditional probability? Now I'm in trouble. So now I would love to assume independence. If I have independence, then I can use the simpler rule for independent events at the bottom of the slide. 0.9 times 0.9, 0.9 squared is 0.81. But if I cannot assume independence, then I need more data. Now what is it? If you ask engineers like to talk about the so-called bathtub curve. A new machine often has breakdowns because it isn't perfectly calibrated, so the probability is maybe a little elevated, and a machine working well for a day or 2 or 3 indicates that the machine is calibrated and the probability changes. It reaches a low, it remains constant for a while, and eventually, due to wear and tear, it goes up. In the middle range, independence is an okay assumption. But at the front end and at the bad end, it isn't. So here we already see how a very trivial application of multiplying probabilities can result in rather tricky issues. Do we have independence or do we not have independence? And that's crucial for our calculations. And as I said, we will see more cool examples in lectures to come. Let me wrap up this lecture. We have seen the general multiplication rule for conditional probabilities. Under the special case of independence, this multiplication rule greatly simplifies, but be careful assuming independence. Thanks for your attention. Please come back for more fun with probabilities. Thank you. Welcome back to an intuitive introduction to probability. In this lecture, I want to tell you about probability tables. Why do we use tables? So far, our calculations were always on rather small examples. There was an A and a B, an intersection of A and B, and so on. Often, however, we want to look at probabilities in more complex examples, and we have many different probabilities. We need to order them. We need to do some accounting and get some structure on them. And that's what probability tables are good for. Let me show you a first example of data. Here we have from a most recent year where complete data is available, the number of foreign visitors to Switzerland. Our friends in Australia and Oceania may forgive me, I left you out because your numbers weren't that large. So let's divide the world into 4 continents: Africa, the Americas, Asia and Europe. Visitors in Switzerland can stay overnight either in a hotel or in another destination. Another destination could be a caravan, could be a camping ground, it could be a youth hostel, it could be France, it could be a private house or private apartment that people rent. We see here in this particular year, there were about 28.3 million visitors in total. At the bottom, we see the totals of overnight stays by foreign visitors from the 4 continents. Not surprisingly, most visitors came from Europe. Switzerland is in Europe. And fewer people came from other continents where you effectively have to fly. We see that about 17 million overnight stays were in hotels, and a bit more than 11 million were in these other domiciles. Now, I think you agree with me, this table is a mess. We see these long numbers, we have numbers between 50,000 and 28 million. It's difficult to sort of look and understand this. So, this table of raw data, of counts, we typically like to translate into proportions, and then we can also use them as probabilities, using, once again, concept number 2, empirical probabilities. Here in the bottom right hand corner, with the green shade, there's always a 1, 100%. How do I get this data? If you look at the accompanying Excel spreadsheet, you will see you just divide every number by the total. 28.3 million was the total divided by itself, gives me this 1.000. We see that 60% of all overnight stays were in hotels, 40% were other. Those together, 60 plus 40, gives me the 1. At the bottom, we see the percentages for the 4 continents. 1.2% for Africa, 7.5% for the Americas, 7.1% for Asia, 84.2% in Europe. You add those numbers up, and guess what? We are back to 100%. In the middle, we see now intersection probabilities. For example, the upper left-hand corner, hotel and Africa, 0.010. So 1% of all overnight stays were by visitors from Africas in hotels. And we have 8 of these intersection probabilities. Here now a little bit of lingo from these probability tables. The numbers in the margins of the table, so at the very right column and the very bottom row, are called marginal probabilities. Here for hotel we would say P of hotel is 0.6. At the bottom, the P of Americas 7.5%, P of Asia 7.1%. So people in probability theory are not very creative or imaginative. These are indeed the margins of the table, and that's where the name came from, marginal probabilities. In the interior, in the middle, we have these intersection probabilities. As I mentioned before, probability of hotel and Africa, 1%, probability of other and Europe, 38.1%. These intersection probabilities in the interior are called joint probabilities because we're looking at joint events of hotel and Africa joining and both happening together. That's the motivation for the choice of the name. You can now scale this as far as you want. So it doesn't have to be just 2 by 4. You can have as many rows as you want. Here I use a generic M. So we have A1, A2 all the way to AM. You can have as many columns as you want. Here I use a generic K, B1, B2 to BK. Here's a requirement that these events must satisfy. A1, A2 all the way to AM need to be what's called mutually exclusive. We have heard that before in the term of disjoint. So they can't happen simultaneously and they need to be collectively exhaustive. So here you either stay in a hotel or in other. Or you are from the Africa, the Americas, Asia or Europe. No other possibility. So that's what it means to be completely exhaustive. Mutually exclusive means either one or the other happens. So don't tell me, oh, I smoked but didn't inhale. That's nonsense. Either you smoked or you did not smoke. So there's an empty intersection and everything is covered. And then we have the joint probabilities, these intersection probabilities in the interior. The probabilities in the margins, the marginal probabilities, are then the sums across the rows or across the columns. And so here now, let me show you this. If you look at the first column, the Africa column, 1% plus 0.2% equals 1.2% in the total. If you look at the row of other, we have 0.002 plus 0.011 plus 0.007 plus 0.381. The total is 40%. So the margins is the sum of the interior. Now, probability tables are very helpful to show us the marginal or total probability of an event, probability of hotel or probability of Asia, and it's great at showing us these intersection probabilities. What these probabilities tables do not show us are conditional probabilities, but those we can now really easily calculate. Let me show you how. What is the probability that an overnight stay in other is from a person visiting from Europe? What do we do? Remember the conditional probability definition. Take the intersection probability and divide it by the probability of the event that occurred. So here, the probability of Europe given other, take the intersection probability, that's a probability in the middle, in the interior of the table, and divide it by the appropriate marginal probability. Here we learn more than 95% of all overnight stays in other, in caravans, in camping grounds, in vacation houses or apartments, in youth hostels is from European visitors. And here in the table, notice what we did. We took the 0.381, the interior probability, Europe and other, and divided by the probability of other, 0.4. So you can just take the element from the interior of the table, divide it by the marginal probability, and voila, there's your conditional probability. We can also go in the other direction, other given Europe. So, what is the probability that a European visitor will stay an overnight in other? So now Europe is given. Probability of other given Europe is what we're looking for. And now we take the same intersection probability, but we're dividing by the marginal probability in the bottom row, the totals. So 0.38 divided by 0.842, and that gives me 45%. To sum up, why do we use probability tables? Things can get very quickly very ugly if we have many different events. So we need to learn to structure the representation of probabilities. Probability tables are a great way to do this. That's why we use them. In the probability tables, we see marginal probabilities and joint probabilities. And so that's why we needed to talk about these concepts. We will use these probability tables for more calculations in the next few lectures. Thanks for your attention and please come back. Welcome to the next lecture on conditional probabilities in the course An Intuitive Introduction to Probability. In this lecture we will learn about Bayes' rule, a rather complicated looking formula that has many applications. But don't worry, you don't actually have to use a complicated formula or memorize it. I will show you how we can easily do the calculations in probability tables and how it's actually rather easy to do the relevant calculations. Before we look at an ugly formula, let's look at a small simple example to introduce some ideas. A company has three suppliers, S, T and U. These parts that these suppliers deliver to the manufacturer, to our company, are either good or defective. For the sake of discussion, let's call them bad parts. Good parts have a probability of 90%, the opposite, bad parts, have a probability of 10%. The company looked at some recent data to see, is there any difference between our suppliers S, T and U? And here's data. Among the good parts, 60% came from S, 25% from T, and the last 15% from the supplier U. Among the bad parts, 40% came from the supplier S, and 30% each from T and U. And now our manufacturer is asking the following question. Which of my suppliers delivers the best parts, the fewest defective parts, the fewest proportion of bad parts, and which is my worst supplier? So in the language of probability, it's asking the following question. What's the probability of a good part given that it comes from supplier S? What's the probability of a good part? It came from T. What's the probability of a good part? It came from U. We can't answer that question yet because let's look at our data. Our data set tells us something different. We learned probability of good, 0.9, probability of bad, 0.1. And then the other probabilities are conditional probabilities, but they're the wrong way. We have the probability of S given good because we were told among the good parts 60% came from S and so on. At the bottom of the slide you see the other numbers. But what we are interested in is probability of good given S. So what should we do? Let's create our probability table with the data that's given. Notice we have good and bad parts on the one hand, and we have three suppliers, S, T and U. Good and bad, we have given these numbers, 0.9 and 0.1. So we can fill in the right margin of our little table, and the sum definitely should be 1. In the interior, we can now use the general multiplication rule for dependent events to create the intersection probability. For example, the probability of a part good and S is 0.6 times 0.9. And so on, all the way to probability of bad and U, 0.3 times 0.1. So we can fill in all the probabilities in the interior, add up every column, and what do we get? Voila! There's our complete probability table. So we see 58% of all parts are from supplier S, 25.5% of all parts are from supplier T, and the remaining 16.5% are from supplier U. Now we can calculate the probabilities we really care about. Here we go. Probability of good given S. Remember how we do this. We take the probability from the interior, in our case 0.54, the joint probability, and divide by the marginal probability of supplier S, 0.58. And what do we learn? 93.1% of the parts that come from supplier S are good. Or more formally in the language of probability of good given S is 93.1. You see all the calculation, and what do we learn? We see that the proportion of good parts is the largest for supplier S. Put differently, the proportion of bad parts is the smallest for supplier S. And supplier U actually is the worst in this little case. So, what did we actually just do? We flipped the conditional probabilities. This casual language of flipping probabilities around is actually very popular among people in probability theory, and so that's why I use this everyday language. So we were given the probabilities S given good, U given bad, and so on. And in the end, we calculated the reverse conditional probabilities of good given S, good given T, all the way to bad given U. And this, now actually there's a very general approach of what we did in this little toy example. There's actually a general rule which does exactly what we just did. And that's this famous Bayes rule. Let me derive it for you. Recall the general multiplication rules that we saw before for conditional probabilities, which is intersection probability equals the conditional probability times the probability of the condition. If we use this and once use the event B as a condition and once use the event A as a condition and then set these two right-hand sides equal, we see the formula at the bottom of the slide in purple. The probability of A given B equals the probability of B given A times probability of A divided by probability of B. Notice on the left we have probability of A given B, and on the right we have the probability of B given A. So if you give me B given A and the marginal probabilities, I can flip around the condition using this formula. Now we can go a step further and say, well, sometimes you may not have the probability of B, and in that case, and that's actually what also happened in our little calculation, we can calculate it by adding up the elements in a probability table. Here, for completion, I give you the formula at the top. If we now take this formula and put it into the flipping formula, we get the formula at the bottom in the with the yellow background. And that's the famous Bayes rule for two events. In our case, we just have had good and bad, or in general language, A and A complement. And what this Bayes rule says, knowing the conditional probability of B given A and B given the complement of A, we can flip around the conditionals and calculate the probability of A given B, and we could also calculate the probability of the complement of A given B. There's nothing special about our example, good and bad, or A and A complement. This scales up. Remember, our probability tables can be as large as we want, and the same is true for Bayes rule. So if we have now M, not just two, but a larger number M of mutually exclusive and totally exhaustive events, then here you see the formula scales up. And as you see, it looks kinda ugly. And so this formula usually scares my students, and so I learned over the years to de-emphasize the actual rule and this nasty looking formula, and sort of teach this via simple examples. As the example I showed you at the beginning, the best way is fill in the probability table and then ask yourself, which conditional probability do I really need? Calculate it using the definition of conditional probability, and that's essentially your applying this complicated looking formula. Let me wrap up. It is possible to flip these conditional probabilities around to go from A given B to B given A. The famous formula behind this is Bayes' rule, but I strongly encourage you build a probability table and calculate the probabilities this way. This concludes our module on conditional probabilities. As I said at the beginning of the module, this is not an easy concept. I showed you a few examples. In the next module, I will focus very much on the concepts of conditional probabilities, dependence and independence in the context of some real-world problems. I could say real-world disasters that happened. And you will see that these concepts, maybe you still think they're very abstract and you think of saying, do I really need this in everyday life? The answer is yes. Yes, and I will show you some cool applications. So please come back for our next module. Thank you very much and enjoy the session with the TA on calculating some probabilities.
Hello, and welcome to the second module of this online course. Today we are going to continue with the Star Wars exercise that we started in the past module. What we have here is that after calculating the probability of escaping through the laser beam, the android R2-D2 realizes that he didn't take into account the laser beam of the enemies that would try to attack the Millennium Falcon to escape the asteroid field. Therefore, R2-D2 needs to recalculate the probability of safely going and flying through the asteroid's field, taking into account that the enemy's laser beams might actually hit the Millennium Falcon and damage it, such that the probabilities of successfully flying through the asteroid beam would be changed. For this, R2-D2 uses a contingency table which has data of past escapes, historical past escapes, that he will use to reproduce his probability of escaping the asteroid's field safely. You can find your contingency table in your documentation, and here you see the historical data of past escapes. So we see that from those who survived the asteroid's field, which are a total of 39 spacecrafts, 37 managed to avoid the laser beams, and 2 were hit by the laser beams. This means that on the way from the place where the aircraft is to the asteroid's field, 2 spacecrafts were hit by laser beams, 37 were not hit by these laser beams, and 39, total of them, could escape through the asteroid's field. Then we had also historical data about the spacecraft that actually crashed in the asteroid fields. And from this we know that 63 out of them could avoid the laser beams. 93, however, were hit by the laser beams. In total, we have 195 escapes, from which 156 crashed in the asteroids, 39 survived in the asteroids, 95, what we see here, were hit by laser beams, and 100 could avoid the laser beams. Well, taking this contingency table and this information, we are now able to answer the specific questions. So the first question is, what's the marginal probability of being hit by a laser beam? Well, we can calculate this probability as 95 divided by 195. Why do we make this calculation? Well, it's easy. We take the total number of escapes that we have, 195, and we select, or we divide by this 195 those who were hit by a laser beam. So if we could go back to our table, and we see here that we have 95 spacecrafts that were hit by a laser beam, out of 195 total that we have in our dataset. So 95 divided by 195 would give us this 49%. Similarly, we can try to answer the second question. What's the joint probability of surviving the asteroids and avoiding the laser beams? Well, now we have to calculate the probability of 2 events. Actually, the probability of surviving the asteroid and the probability of avoiding the laser beams. So the favorable cases that we will have to divide by the total cases in this case are those in which the spacecraft survives the asteroids and those in which they avoid the laser beam. So if you go to the contingency table, you will be able to see that this number is 37. So if we divide 37, which are of favorable cases, by the total number of cases, 195, this yields the probability of surviving and avoiding the laser beam, which is 19%. Now we can increase a little bit the difficulty of the question and ask, given that the spacecraft is hit by a laser beam, what's the probability of being alive after crossing the asteroid field? Well, in this case, we know for sure that the spacecraft is hit by a laser beam. So this reduces the relevant state space that we can, or that we have to use to make our calculation. In this case, it's the relevant state space is reduced to 95 cases. Actually, those in which the spacecraft is for sure hit by the laser beam. Then we take the favorable cases again, which is those in which the spacecraft survive. We see it's only 2 in the contingency table. So if we divide 2 by 95, we get the probability that we are looking for, which is 2.1%. Now we can scroll down a little bit and try to answer our last question, which is also very similar to the previous one. Now, given that the spacecraft escapes the asteroid field, what's the probability of having been hit by a laser beam? So now we see again that the relevant state space gets updated again to the cases in which the spacecraft survives the asteroids, or the crossing of the asteroids field, which is 39 cases. We would then take our favorable cases, which would be those in which the spacecraft manages to escape the asteroid field, which are only 2, and then divide it by our relevant state space, 39. This would give a probability of 5.1%. Well, thank you very much. I hope that you have learned a little bit more about how to handle some probabilities and that you have enjoyed the module. See you soon and have fun.
Welcome to our next module in an intuitive introduction to probability, decision making in an uncertain world. In this module, I want to show you a bunch of applications of probabilities. As I said at the very beginning of this course, many people tell me I hate probability. And I think that attitude comes from that many people don't really see cool real-world applications that are really relevant in everyday decision making or relevant to the well-being of our societies. And here I really want to convince you that there are cool applications. We're going to start with some playful applications. Today, in the first lecture, we're going to look at the birthday problem. And then later on, we get into some more serious stuff from business or the law. So let's just dive into the birthday problem. What is that about? You go to a party and there's a bunch of people in the room. And here's now the question. What is the probability that there's at least one pair of people at this party who have birthday on the same day of the year? 2 people having birthday on January 18th or March 22nd or July 1st. And then a related question. How many people do you have to have at this party so that this probability of at least one pair of birthday people in the room is larger than a half, larger than 50%. These 2 questions together give us a birthday problem. Before I tell you how to think about this, here's an in-class quiz question for you. Let's go back to the second question. How many people do you need to have in a room so that the probability of at least one pair is larger than 50%. Here I have a bunch of options of possible answers. Exactly one of them is correct. Please have a go at it. And then afterwards I will tell you how we can calculate these probabilities. Welcome back from the in-class quiz question. Now I want to show you how we can calculate these probabilities. I've prepared an Excel sheet called birthday problems. Now, before I show you the calculations in that sheet, I want to tell you a little bit about the strategy on how we calculate the probabilities that I mentioned before. It's actually a really tricky question to think about how many people may have birthday on the same day, because maybe there's one pair, maybe there are two pairs, maybe there are three or more pairs, maybe there are triplets. There's so many possibilities that it quickly gets totally overwhelming. And I can tell you, I have no idea on how to calculate this probability that way. But I can show you a much more elegant, much simpler way. Let's use the complement rule. Remember, this was one of the key rules that we learned about in the very first module. So, the probability of the complement of an event is 1 minus the probability of the event. What's the opposite of having at least one pair? Or two pairs or so more? The opposite is very easy, very well defined. All of us at this party, all the people in this room having birthday on different days. And it turns out that probability can be calculated quite easily. So now come with me to the Excel sheet and I'll show you how we can calculate that probability. Here we are now at the spreadsheet for the birthday problem that I prepared. Before we get into the calculation, I need to state my assumptions, which are listed over here in column E. First, we assume there's no February 29th, so we assume there are only 365 days in a given year. All of those days are equally likely, and we assume all the people in the room are independent. That means your birthday doesn't affect mine, our birthdays don't affect anyone else's, and so on. And as I now said before, we're not yet calculating the probability of the event we really care about, that there's at least one pair. Instead, we're looking at the complement. What's the probability that all of us in the room have their birthday on different days? We look at person 1. Person 1 can choose his or her birthday any day in the year. It gets interesting with person 2. This person now has only 364 out of 365 days left. Why? The first person picked a day, that's my birthday, and now we want the second person to be different. That leaves only 364. And so now I start calculating these probabilities here. 1, anything goes for the first person, times 364 divided by 365. So this number here, the 0.99726, is a probability that a pair has birthday on different days. Now the third person enters the party. What's the probability that her birthday is different than of the first two people? 2 days are taken in the year. That means 363 days are left. So we multiply with 363 divided by 365 and get this probability, a little less than 99.2%. You now see, as more and more people enter the room, the probability of being different gets a little smaller, and independence, we multiply all of them. And so now what happens is that this product gets smaller and smaller and smaller. Now the amazing thing here is that the probability drops below a half already at 23. So as soon as there are 23 people in the room, and assuming our assumptions apply, then the probability of all of us having birthday on a different day is already below a half. That now means with 23 people, the probability of at least one pair is larger than a half. That's very counterintuitive and quite surprising. So often people tell me this can't be true. How can this be? Now I calculated probabilities for many other numbers, including 45. 45, it's under 6%. And now for 45, I also prepared a Monte Carlo simulation. How does this work now? Let's go here to the second sheet. Here now I randomly pick 45 numbers, and that's very easy in Excel. There's this cool function rand between, and then I do 1 semicolon 365 here on this Swiss computer. In the United States it's 1 comma 365, whatever it is in your language, and this gives me a random number between 1 and 365. I do this for all 45 people, and then I compare look at all pairs. So here I compare person 2 to person 1. I compare person 3 to person 1 and 2. Here I compare person 10 to the first 9. If I see a match between person here for 8 and 5, as I indicate here, then I get a 1. Otherwise, the spreadsheet shows me a 0. Now at the top here, I count the number of matches that we have in our spreadsheet. And now I can recalculate the sheet, either by clicking a button here or on a Windows computer, easily F9. And I create 45 new birthdays, a new party, 45 new people, and I check, is there a pair? Look at this, right now I have 2 pairs. And so yes, there's at least 1 match. I do it again, 3 pairs. I do it again, another 2 pairs. 2 pairs, 4 pairs. Wow, look at this. 3 pairs, 1 pair. Now, you see, it's hard to hit a 0. Do it for a while and eventually you will also occasionally hit a 0. I can tell you in less than 6% of all times. Before I return the spreadsheet, I want to do one last detour. People find this so strange. How can it be that with 23 people, we already have a likelihood larger than a half of having a pair? Now, let me go to the third and last sheet on my Excel spreadsheet here. Now we change the problem. Here the question is now, what is the probability that at least 2 people have a birthday today? Or the complement, that nobody of us has a birthday today. This is a fundamentally different problem. Why? I fixed the day. I said, let's look at birthdays today. This now rules out you and me having birthdays on the same day of the year. That's different than today. That's in the previous version of the problem. That was a hit. That was a match. That was a pair. And there are so many days, 365, where you and I could have a birthday together. Here now, that birthday has to be today. Now the probability calculation changes. Here's now, notice the different definition. Now we're looking at the probability that all of us do not have a birthday today. Now for each of us, the probability of not having a birthday today is 364 divided by 365. It doesn't decrease. You and I can have both birthday yesterday. That is still not a match here. So now the probability, as you see here in my spreadsheet, is 364 divided by 365 to the power of the number of people in the room. Independence. Your probability, not today, 364 divided by 365 times my birthday not being today, 364 times 365 times so on for all of them. And now you may think, oh, I need 183 people for this to be 50-50. Why do people think this? Oh, that's 365 divided by a half is 182.5. So with 183 people, this will be about a half. Wrong. Because from those 183 people, quite a few will have birthdays on the same days. And therefore, it's not that we have covered half a year for sure with 183 people. Actually less. You can now play with this, and the surprising result here is that you need 253 people at your party to have a probability of more than a half that at least one of them has a birthday today. That's a very different calculation. So let me sum this up one more time. In this last instance of the problem, the question was, what's the probability that we have someone having a birthday today? So today and a person's birthday matches. That's very different than in the original birthday problem at the beginning here, where it can be any day of the year. And so I think this helps a lot of people to get over this counterintuitive result that you only need 23 people to have a match on some day a year. Not today, on some day of the year. So this wraps up the Excel spreadsheet discussion. Play around with it a little bit more if you want. And now let's summarize everything in the slides and return there. Here we are back from our Excel sheet. Let me briefly summarize our calculations. We made the following assumptions. There are 365 days in a year, so we are ignoring February 29th. We assume that all days are equally likely, and finally, that we are all independent of each other. Your birthday doesn't affect mine, nor anyone else's in the room. And then we just saw the probability now of the complement of the original event, namely all of us having birthday on different days, is one big long multiplication. The first person can have birthday on any given day. The second person now needs to be different. The first person has taken a day, for example January 1st, so the second person has 364 out of 365 days left. So I multiply 1 times 364 divided by 365. Now the second person comes along. In addition to the first, so in total the third person. Now this person cannot have birthday on the first 2 days that person 1 and person 2 had a birthday on. So that's 363 out of 365, which we multiply with the previous product, and so on. And now you go until however many people are in this room. To summarize, here are the results. On the one hand, with 10 people, there's a more than 88% chance that all of us then in the room, if there are only 10 of us, have birthday on a different day. With 23 people, that already drops below a half. Put differently, for the original event that we talked about, what's the probability of having at least one pair? With only 23 people, that probability already exceeds a half. So the answer to that quiz question was 23, the smallest of the choices given. Now notice, once you have 60 or more people in the room, the probability of all of them having different birthdays drops below 1%. So that means next time you're at a party, you may want to offer that bet. I think you will be able to surprise some people. And that already brings us to the takeaways. In addition to this rather surprising, perhaps counterintuitive result of the birthday problem, we also have seen an application of the complement rule. The complement rule sometimes can be very, very helpful when the calculation of the probability of an event is very, very tedious. Always think maybe the complement rule allows me an easier calculation. That's the first application in this module. Come back for more fun in the next few lectures. Thank you. Welcome back to this module on applications of probability. The next problem is another playful application of probability, the famous, some people may say infamous, Monty Hall problem. So, what is this problem about? Congratulations, you're the winner of a game show. You beat all the other candidates on this game show. It's the final moment for you to win a big prize, a brand new car, or go home with a goat. Here's how this Monty Hall problem works. You stand in front of 3 doors. Behind one of those doors is that brand new car that you can win. Behind the other 2 doors is a goat behind each door. You now get to pick one door. Let's say you pick door 1. Now, the game show host gets to open one of the other doors. He is not allowed to open the door that you picked, and he's not allowed to open the door with the big prize. He must open a door with the goat, or with a goat. And now the game is back to you. So he opens a door. Let's say he opens door 3, and behind door 3 is a goat. You pick door 1. Now, you get to decide. You can keep door 1, or you can switch to door 2. And then the prize is revealed. Either you're the lucky winner of a brand new car, or the not quite so lucky winner of a goat. And before I tell you what to do, here's the in-class quiz question for you. What should you do? Should you keep door 1, the door you originally chose? Should you switch to the other remaining closed door? Or it doesn't matter? So, What do you think? Did you think about this problem? Did you switch? Did you stay the same? Did you say it's 50-50? Doesn't matter? Now, you should switch. The answer is the probability of staying with the same door, you have a probability of 1 in 3 to win. The probability of switching to the other door is 2 in 3. So you can double your chances of winning by switching to the other door. Let's think about why that's the case. Let's go back to the beginning of the problem. There are 3 doors. You have no information. So all doors, I think we can agree, are equally likely. That's wonderful. We can use the definition number 1, the classical probability definition, or the objective definition that we've learned about at the very beginning of this course. 1 in 3. So the probability that you pick the right door, no matter which door it is 1 in 3. There's a probability 2 in 3 that you're picking the wrong door. I think we can all agree on this. 1 in 3, 1/3, 33 and a third %, you are right. 2/3, you have the wrong door. Let's think about this now. The 2/3 probability. That means there are 2 doors where there's a prize. But the prize can only be behind one door. So there's either the prize is behind door 2 and a goat in door 3, or the other way around. So the 2/3 probability includes the fact that behind one door there must be a goat, because there's only one car, not 2 cars. There must be a goat among those doors that you did not choose. Now the game host, the showmaster, shows you that door and that goat. You just didn't learn anything. Nothing changed. Your original probability was 1/3. The original probability was 2/3 that it's behind one of the other doors, and that included one goat. There's nothing has changed. The game show host just made your life easy now, because that 2/3 is now essentially on that one remaining door. And therefore you should switch. Many people find this very counterintuitive. So let me try to give you another sort of explanation. Let's think about there isn't one door or 3 doors, but in fact there are 100 doors. 99 goats, 1 car. You pick again any door. Let's say again door 1. What's the probability that the car is behind that door? 1 in 100. Very unlikely that you pick the right door. Now the game show host opens 98 doors. Now think about it. 98 goats. Yeah, you knew there had to be 98 goats. Maybe 99 in the unlikely case you already had the car. Otherwise, he can choose. There are 98 doors that he has to open with those dumb goats. So, would you switch now? Yeah, of course you want to switch, because there was 1 in 100 before. It's going to be behind that other door, most likely. So I think some of the confusion stems from that it's only 3 doors. If you think about more doors, you will think, yeah, I definitely want to switch. I know this is very tricky, so let's now look at a Monte Carlo simulation of this problem in a spreadsheet. And I'm now going to simulate this game 1,000 times, and from the simulation create data, create proportions of winning by switching or winning by not switching, and then let's have a look at those numbers. So now, because we're looking at data, we're back to probability definition number 2. So let's go to the spreadsheet. Here's now a spreadsheet where I simulate this Monty Hall game show problem for you. Let's have a look at what I've done here. First, under price, there's a rand between 1 to 3. So this is a random number between 1 and 3, and that's the number of the door where the price is. So here in this example right now, it's a 2. The candidate chooses a 2. Again, a random number. I assume that the candidate is completely clueless and just randomly picks a number. Then the host has to open a door with a goat. Now here, this is quite a complicated Excel formula. You can ignore this. I know many of you can code this very elegantly and much faster than I did using Excel macros or Visual Basic. I deliberately did not do this here, so this will hopefully run on anyone's spreadsheet, on any type of computer, even older computers in the world. Then we look at what happens if the candidate does not switch, keeps the same door, or what happens if the candidate switches. And then here we see with a simple if question whether he or she wins or loses. Now, if I recalculate my sheet, every time I do this 1,000 times. 1,000 times I say, here's a price, here's a candidate, chooses this side, the host opens something, and then we see what happens with switching or not switching. Here, for example, right now on my sheet, it says, if you do not switch, you win 33.9% of the time. If you switch, you win 66.1% of the time in these 1,000. Now let me click recalculate sheet. Notice the number changed. 34.6% not changing, 65% probability of winning, yes, when you change. Here it's now 30.3 to 69.7. So you see, our relative frequencies are indeed close to the 1/3, 2/3 cutoff that I explained to you earlier. We can't expect that we hit it exactly, but we get very close. And I hope this convinces the last doubters among you that indeed the probability of winning after switching is twice as high as the probability of winning when you don't switch. So if you're ever in that situation, please do me a favor, switch that door. So let's go back to the slides, and I will tell you about some pop culture appearances of this problem. This concludes our look at the probabilities in the Monty Hall problem. As you can imagine, sort of a cute problem like this that comes out of a game show makes its way into popular culture. In the movie 21, there's a really cute scene where a student at MIT has to explain this problem and the solution to his professor. Please Google it and have a look at the clip. It's just 2.5 minutes. I think you will enjoy it. In 1990, there was a lot of controversy about this problem. Namely, a reader of a weekend magazine called Parade had sent in this question to a column called Ask Marilyn. This woman Marilyn is supposedly the highest IQ person on the globe, and she answers all kinds of questions that people have, whether it's in their love life, in their everyday life, or IQ related questions. Now, when she explained this solution and that you should switch the doors and that the probability then is 2/3 of winning, she received a lot of hate mail, and in particular she received more than 1,000 letters from PhDs in mathematics who were ridiculing her answer and said this is complete nonsense, it's a flip of a coin, 50-50. Now, all of them later on had to take their criticism and their laughter back when she then in great detail convinced them of the right answer. And as we just saw in the Monte Carlo simulation, I think there can be no discussion. The true number is not 50-50, it's 2/3, 1/3, and you should change. So here I give you the link of Marilyn's website, and there's a lot of entertaining discussion and a lot of these sometimes hurtful and ridiculously offensive quotes from these math PhDs. That brings us to the end of this second application after the birthday problem in the first lecture. Now we had the Monty Hall problem. This finishes our playful cutie applications. Now we move on to applications from the business world. So please come back for more applications of probability. Thank you. Welcome back to the application module of the course, An Intuitive Introduction to Probability, Decision Making in an Uncertain World. After looking at two playful applications of probability, today in this lecture I want to talk about very serious application where things went wrong. We're going to look at one of the core problems of the financial crisis that happened in 07 to 09. And this has to do with the structuring of risks in finance. Unfortunately, to really hit that point home, I have to introduce a little bit of finance to you. It won't be too much, but I need a little bit sort of background so you can understand what went wrong in the financial crisis. We need to talk about bonds. What are bonds? When a company wants to do a big project, a big construction project, or wants to build a huge new factory, that company may need a lot of money. More money than it has in the bank. So it needs a loan. Now, one way to get this loan is to get a bank, just like you and I do. When we need a loan, we go to a bank and the bank gives us money and we pay the loan back. Companies now have a second way to do this. They can borrow money from the financial markets, where lots of us give this company some money. And that's done through a bond. So a bond is what's called a debt obligation. So they have a debt obligation to us, the lenders, and that's how we give them money, and in the end they give us the money back. And along the way we hopefully get some interest. Now something can go wrong. The company could go bankrupt and then default on its loan, meaning it does not pay back the loan. So that's very bad for you and me. If we gave that some of our money to that company and then they default on us, we're going to be mad because they don't give us money back. Now, let's now look at a black and white scenario. No default, we get our money back, or default, we get no money back. Now, since we don't know the inner workings of these companies, we, or investors in general, rely on so-called rating agencies, which give ratings to these bonds and tell them, oh, this is a safe investment, or this is sort of a more risky investment. These companies get so-called credit ratings. The best ratings is a AAA, AAA. That's the best you can get. Then it goes down all the way to CCC. To simplify the discussion, we're going to have very good bonds called investment grade bonds that are considered quite safe, and risky bonds, sort of the junk bonds. Now, these ratings are very important for the companies for at least two reasons. One, the larger the rating, the safer they are considered, the less interest they need to pay us. We, of course, are more comfortable giving our money to a very safe company than to a risky company. Secondly, some investors, some institutional investors, such as pension funds, are only allowed to invest into safe bonds. So these ratings are very important. Here is some historical data on these ratings from a rating agencies. We can think of these now, equilibrium concept 2, once again, empirical probabilities. AAA bonds, for example, it's very unlikely that they default, a probability very close to 0. The same is still true for AA+, and you see it gets gigantically large for really bad ratings such as Cs. So, now we want to understand how these ratings affected the financial crisis and what happened in the financial crisis. In the financial crisis, or before the crisis actually happened, these risks, these bonds got pooled. In particular, for those of you who have followed the crisis, there was something called a mortgage-backed security, where these debts were actually the debts of house buyers who bought houses, they needed money, and then lots of these home loans were put together in the funds of these bonds. So now I want to show you how with junky bonds that we put together into a portfolio we can create some good risks. So here now let's think about that we have two bad investments, two risky investments, two junk bonds. let's call them X and Y, and they both have a probability of default of 10%. So there's a 10% chance we're going to lose our money. We're not going to be happy about this. And now what people in finance do, and what's at the heart of the financial crisis, they take these junky bonds together and create a new type of asset based on those that's supposedly very safe. And so, make some junky stuff into really safe stuff. Now, now let's move towards probabilities. We have two investments. In both investments could either lead to a default or no default. Now we have actually 4 combinations in total. The first investment, default, no default, characterized by little d or little n. Second investment, also a little d or little n, and any pairs possible. DD, both x and y default, dn, x defaults, y does not default, and so on. And remember, we have these probabilities, 10% default, 90% no default. What can now happen to a portfolio if you think about those debts together? When both default, no money comes back. 0, 0 in the sum, the two junk bonds pay 0. If one of them does not default, the other one defaults, the payback is 1. And in the best case scenario, neither of them defaults, both pay back all the money. We get $1 back on each case, gives us $2. Now let's assume those are independent. So the question is, how likely are these 4 possibilities? With independence, we can use the multiplication rule that we learned about in independent probabilities in the first 2 modules and create this probability table. Here in the probability table, you now see the probability that x and y defaults, the intersection probability in the upper left-hand corner of the table, equals the probability of the product of the marginal probability, 0.1 times 0.1. So there's only a 1% chance that both of them default. You do the similar math and you can fill in the table. So let's now do the following. We are now taking the money that comes in from X and Y and we return it to the investors. But we do so in a very special way. We create new investments, I and J, an investment grade and a junk bond. And how are those defined? Look at these 2 tables. On the left, we see the money that comes in from our 2 original junk bonds, X and Y, 0, 1 or 2. And now we split this according to the following rule. And this rule is actually written down by lawyers on paper. The rule is the following. The first dollar that comes in goes to asset I. Any remaining funds go to asset J. Let me repeat this because this is crucial now. The first dollar that comes in, no matter what, goes to I. Any remaining funds go to J. Now let's look what that means. First case, X and Y both default. Nothing comes in. So nothing can go out. I pays 0, J pays 0. The next 2 scenarios, exactly $1 comes in. So who gets the first dollar? The rule says asset I. So asset J again gets nothing. Finally, in the good case, $2 come in, both I and J get $1. Now look at the sum of I plus J. It's exactly the same as X plus Y. So let me emphasize, there is absolutely clean accounting. There's no cheating, no money being hidden, no money being added. Whatever X plus Y pay in are paid out via I and J. But boy, are I and J different here. Look at I. I pays in 3 out of the 4 cases. It only does not pay in the default case, which has a tiny probability of only 1%. So I suddenly looks pretty good, only a 1% chance of default. That's a very good bond that gets a high rating. It has a 99% chance of paying off. So it has investment grade status. Even though X and Y, the ingredients in this financial alchemy, are junk bonds. But because of this split up, of this legal contract of splitting up the money that comes in this peculiar way, I become safe. J, on the other hand, look at J. J only pays in the best case scenario of no default, no default. In all of the other 3 cases, there isn't enough money coming in. Because either no money is coming in or the money that's coming in goes to asset I. So J is super junk, or how the pros in finance call it, toxic junk. So what happened here? We get junk plus junk, X and Y, and out of it we get a very safe asset I, and we get the toxic junk J. And that's what structured finance is all about. Now, you may have heard or read in the newspaper the term collateralized debt obligations. This is a multi-trillion-dollar. And by the way, this is not a typo. I'm not talking about millions or billions. It's trillion-dollar market. These are thousands of billions. And in finance, banks do this with mortgages, car loans. In countries where you have student loans, this is done with student loans, credit card debt. This is a gigantic market where people take group debts together and cut it off in these what's called tranches. Now, I know this was a heavy module. I gave you the basic idea of structured finance, how we pool risks together and then create new risks with different risk levels. Remember, junk plus junk gave safe plus toxic junk. But did you notice a probability in here? We assumed some independence. And that was a crucial mistake the rating agencies made in the financial crisis. They relied on this independence. And that's why this I looked so golden. In the next lecture, we're going to talk about dependence, when that assumption falls apart. And then all hell breaks loose, as we saw in 2007. Stay tuned for more. The story continues. Welcome back to our discussion of structured finance within the course An Intuitive Introduction to Probability. I showed you in the last lecture on how we can aggregate risks when we pool them and then split them up in novel ways. Here's a quick reminder of what happened. We have these 2 risks, X and Y, that are either default or don't default. We looked at the 4 possible combinations, both of them defaulting, one of them defaulting, or finally neither of them defaulting, and the probabilities: default 10%, no default 90%. I had shown you when we aggregate those, we have these 4 possible scenarios, and with the payoffs 0, 1, 1, and 2. And then we had split them up into the investments I and J. When we looked at the probabilities, and I showed you a probability table, we had assumed independence. Independence meant I can use the multiplication rule and take the probabilities from the margins to get the joint probabilities in the inner portion of the table. Now let's think about these risks to be dependent, that X and Y are no longer independent but dependent. Quick reminder, what does that mean? That means when X defaults, that tells me something about the likelihood that Y defaults. In particular, let's now think about a dependence that's also called a positive correlation, where when one asset defaults, actually the probability of the other asset's default increases. Look at this table now. I no longer assume dependence. Remember the upper left-hand corner in the yellow cell, there used to be a 0.01. The product of 0.1 at the bottom left times the 0.1 on the top right. Now let's assume that's wrong and that actually the joint probability is 0.06. Then you can easily fill in the other probabilities. Now let's look at what happens to the investment grade asset I because of the dependence. Now the probability of DD, default, is no longer 0.1 squared, 0.01. Now it's 0.06. So now it has a much higher default probability. Actually, it's so high, it is no longer an investment grade asset, it's now a junk asset. On the other hand, J, which before was toxic junk with a gigantic probability of default of 19%, is now actually slightly better. What has happened? We have junk X plus junk Y, we mix them up into I and J, and it's still junk plus junk. There's no gold. This investment grade I that we had before no longer exists. I is junk too. Now, this is a result of the dependence. Here we have a specific dependence called positive correlation that we will take another look at in the next module. So, the investment grade asset I actually has now a lower value and a higher probability of default as a result of the dependence. So the investment grade asset I is actually much worse now than under the case of independence, while for the junk bond J it's the other way around. The toxic junk is a little less toxic. It's still junk though. Now, why do you have correlation there? For example, if you think companies that are in the same business or in the same industry, if somehow this industry is not doing well, everyone is doing poorly. Or on the other hand, when that industry is doing very well, everyone is doing well. So you have these companies either both all doing well or all doing poorly. In Switzerland, we had this now after the Swiss National Bank stopped the peg of the Swiss franc to the euro. That was a very bad hit to all exporters and in particular also to the tourism industry in Switzerland. That was actually bad for all of them. So there was a dependence through what economists call an exogenous shock. In this case, an exogenous negative shock. And when this happens, and this typically happens in crises, as we had in the financial crisis in 2007 to 2009, we suddenly have the dependence. And then this idea of structured finance, taking junk together and creating some good safe assets that's good enough for you and me as a retail investor or for a pension fund, and toxic junk for the pros and the gamblers, that breaks apart. Junk plus junk is still junk. And so that's at the heart of what happened. Actually, there's great literature on there. If you Google this, I have here a particular highly cited economics research paper with a beautiful quote. And here I highlighted the last sentence. So the problem why the rating agencies misrated and underestimated the risk in some of these assets was exactly this, that there was this dependence among the risks. They had assumed independence ex ante, but later the risks were dependent. And you saw the importance between independence and dependence. And we will see that problem again and again as we move ahead through this course. To summarize, the basic idea of pooling risks in structured finance fails terribly when the risks that you pool have a strong dependence. And this particular issue contributed greatly to the financial crisis of 2007 to 2009. There were lots of other issues. There was some cheating going on, some misreporting, there were other problems. However, this particular probability issue clearly contributed to the financial crisis. Now, taking a step back from this particular finance application, the bigger lesson for us is independence versus dependence is a huge issue in probabilities. And so when we multiply probabilities, we always have to ask ourselves, is the assumption of independence justified, yes or no? And if the answer is no, we cannot multiply probabilities. Then we need to think about conditional probabilities. So this wraps up our 2 lectures on structured finance. Now we're going to switch gears entirely and look at law, and in particular cases in courts where probabilities are often misinterpreted. Thanks, and please come back for more applications of probabilities. Thank you. Welcome back to the module on applications of probabilities. As I promised you in the last lecture, we're now switching gears towards applications in the courtroom. A famous problem in legal issues is the so-called prosecutor's fallacies. At the very basic, it's a mistake in logical thinking. And in particular, in our language, in probability, it's a confusion between the probability of A given B versus the probability of B given A. Essentially, the question is what has happened already and what's still uncertain. Remember, probability of A given B means condition B holds. What's the probability of A happening? A is still uncertain. B has happened. While in the other way around, probability of B given A, we know A has happened, A is known, but B is still out there, is uncertain. What's the probability of B happening? And this difference can lead to terrible misjudgments. There's a whole legal history now on issues or on cases where this got screwed up. In particular, it's important in the evaluation of evidence, for example, in DNA comparisons among possible culprits in a crime. First, I want to explain to you the problem in sort of our language of probability and conditional probabilities, and then we're going to look at an example from legal history. Here's the question. We have a defendant in court. Is he or she innocent? So the event I says the defendant is innocent. The opposite, I complement, is guilty. So let's just look at innocent versus guilt. Nothing in between. So don't tell me, oh, I smoked but didn't inhale. No, that doesn't exist here. Innocent versus not innocent. I complement. And then there's the issue of what I call the DE, the damning evidence, the really bad evidence that we have and why we're in court. This could, for example, be the DNA match at the crime scene. Now let's look in our language, what do the 2 different conditional probabilities mean? First, the probability of the damning evidence given the person is innocent. So that's a probability that an innocent person, so that's what we assume, we know person is innocent, matches the damning evidence. Whether he or she matches the damning evidence, that's now the uncertain part, that's where we still have a probability. Now let's think about it the other way around. What's the probability of I given DE? The probability of being innocent giving the damning evidence. That now means we have a person who has the damning evidence, maybe his or her DNA matches something found at a crime scene. So DE has happened, and now the question is this person innocent or guilty? So that's still out there. Notice the difference between those 2 probabilities. Here's now the heart of the problem. You go to court. A prosecution's expert witness says an innocent person has a 1 in 100,000 chance of matching the damning evidence. And now comes the prosecutor's fallacy. Now the prosecutor says, the defendant has the damning evidence. Therefore, there's only a 1 in 100,000 chance that the defendant is innocent. Clearly is guilty. Jury, judge, I say the defendant is guilty. Send him to prison or her to prison. That's the prosecutor's fallacy, and this thinking is wrong. Let's look at what the expert witness said. The expert witness said the probability of an innocent person, that the person is innocent, has the damning evidence is 1 in 100,000. The prosecutor's fallacy is now to turn this around and say, the damning evidence match is there, that's why now the probability of innocence is also 1 in 100,000. But that's wrong, because in that argument, the prosecutor changed the uncertain statement, that's still uncertain, and the condition around. But those two probabilities are usually different. Now you say, that's a problem. How do we get the other probability? We have Bayes' rule. Do you remember Bayes' rule from this flipping probabilities in the previous model? We actually have at least a theoretical way to go from the expert witness's statement to the probability that the prosecutor, the jury, and the judge care about. Remember the flipping formula. The probability of I given damning evidence equals the probability of damning evidence given I times these two other probabilities, or this ratio of two other probabilities. Now, the question is, what is the probability on the left-hand side? That's really the one. We have found damning evidence against someone, but what's the probability that this person could still be innocent? Or the probability that this person is guilty? On the right-hand side, we have the first probability. That's what the expert witness said. That's a tiny, tiny probability. But wait a minute. This now gets multiplied by a ratio. If that probability of DE is very small, we're dividing by a number that's very small. And a small number divided by another small number can suddenly get a little larger. Let me illustrate this in a simple example. The guilty person is among 500,000 people living in a town. Let's say we know this. Because of circumstantial evidence or timing, someone was robbed or murdered or something. We know, we are down to 500,000 people. And let's make the following assumption. The guilty person left some DNA, or there's some match that that the guilty person also has, and that's our damning evidence. So, here now probabilities we know. And so simplification, let's assume there's a single culprit. There's only one criminal. We don't have a group of criminals that did this somehow together. So there's a single person that's guilty and the rest is innocent. So that gives me the probability of being innocent and the probability of guilty. As you see here, 499,999 out of 500,000. Those are all innocent and that last person is the guilty one. And we know if you're the guilty person, if IC is true, the complement of innocent, IC the guilt, then the probability of showing this damning evidence is 1. Using these probabilities, I can now use Bayes' rule. I can calculate the probability of the damning evidence, and I can calculate the probability of being innocent, giving the damning evidence, and being guilty, given the damning evidence, and you have the probabilities here. So there's a 1 in 6 chance that given the damning evidence has been found, the person is guilty, and there's a 5 in 6 chance that the person is innocent. The calculations are here, you can look at them. So look at this. We find the damning evidence for a person. The probability that he or she is still innocent is 5 in 6. What's the logic here? How can that be? Here's another way of looking at it. Given the probabilities that we have. So we have 500,000 people, and the probability is of any innocent person having this damning evidence here at the first calculation is 1 in 100,000. So let's do simple math. You have 500,000 people and a 1 in 100,000 chance that an innocent person has that same DNA or the same sort of soccer shoe or something that was found at the crime scene. 500,000 people, 1 in 100,000 chance of someone by accident having this. That means in that city you have 5 innocent people who match that stuff, plus a guilty person. That's 6 people who match them. One of those 6 is a bad guy, the other 5 are the unlucky guys. So that's now the idea here, is that because the chance that an innocent person has this damning evidence, even if it's small, if the number is large enough of potential criminals and therefore also potential innocent people, that's how we get in the end quite a large group, in this case 6 potential criminals, but only 1 did it. And so even if you have that wrong DNA, there's still a good chance you are innocent. And that's sort of the intuitive explanation here, that for some of you may be a little easier than just going through the tedious math of applying Bayes' rule. And here I sort of summarize this in a probability table. Perhaps this is a little more familiar for some of you now that we have worked with probability tables. That sort of summarizes all the probabilities. Now, you may think this is kind of obscure and never happens. Sorry, no, that's not the case. If you Google prosecutors' fallacies, you will see many, many examples. I picked out one that's sort of well known now in legal history, a famous one, and that's this group of the so-called Birmingham Six. So, let me tell you a little story. Remember back in the 70s, there was still a lot of or many issues in the United Kingdom between the Protestants and the Catholics in Ireland and Northern Ireland. And there was a terrorist organization called the IRA that organized bombings and killed British people. And in particular, a bad crime happened in the second largest city of England, Birmingham, in November of 1974. There was a bad pub bombing where 21 people were killed and 182 were injured. Quickly, 6 men were found who became infamous as the Birmingham Six in the UK press. And they were found guilty of this murder less than a year later, in the August of 1975, and each defendant received 21 life sentences. The key statement why these people were found guilty is the following. A forensic scientist had said that among these 6 defendants, they all had to do tests, and he was sure up to 99% that 2 out of these 6 Birmingham Six people had handled explosives. So here was his claim in our language. The probability of handling explosive, given that the test, his special test is positive, is 0.99. And people said that's so high, clearly these bad guys handled the explosives and they must be the terrible criminals. Now, it's not 100%, it's only 99%, and because these tests are not correct. In particular, at the time it was known that other substances produce positive test result, including nitrocellulose. I don't know whether I pronounce this correctly. This chemical is present in paint, on playing cards, in gasoline, cigarettes, and soap. Now, here's the problem of what happened. The expert witness already made the prosecutor's fallacy, because what he should have said is the following. If you handle explosives, then the test will be positive. So then you'll come in touch with this chemical and the test will give us a positive signal. But the claim that he made, if the test is positive, that means you handled explosives, seems to be much smaller than many of us on any given day get in touch with gasoline if you go to a gas station. For smokers among you, you may get in touch with this if you smoke. If it's in soap, well, many of us get in touch with that, and other reasons. In particular, the defendants had been caught on a train playing cards. So what happened eventually? After various appeals, finally in 1999 there was a second appeal and they were all released from prison. And actually nowadays people think that these people were actually innocent and that other people, and apparently there's some known names, but these people didn't get convicted for doing the crimes. There were other issues at these various appeals and at these various trials, but at the very heart was this misstatement from the forensic expert who had already done the flipping that he shouldn't have done of the conditional probabilities, and he committed the prosecutor's fallacy. And this is just one famous example of many others in the legal history where people confuse what's given, what have we found, and what's still out there. And what we have found is the evidence or the test result. What's unclear is the innocence or guilt. But people often then argue with it the other way around. Whenever we have a prosecutor's fallacy, that's a neglected application of Bayes' rule. People are forgetting about that they really should use Bayes' rule. Next, and as our last application, in the next lecture I will show you a particularly sad story of a real tragedy where a prosecutor's fallacy led to a lot of harm. So please come back for the last application of this module. Thank you. Now let's talk about the last application of probability in our course, An Intuitive Introduction to Probability. It's a sad story of a woman in England by the name of Sally Clark. The story starts out okay. Sally Clark was born in England in 1964. She married a gentleman by the name of Steve Clark in 1990. They moved to a house near Manchester in 1994. Both of them worked together at a law firm in Manchester. Their first son, Christopher, was born in September 1996. So far, so good. A story like you may have heard many, many times, a happy couple with a baby. And then tragedy struck. The baby falls unconscious in December 1996, so just a couple months old, and dies. Sally is home alone with the boy. Now, the baby shows some signs of trauma, but the doctor thinks maybe while trying to revitalize the baby or bring it back from lack of consciousness, this may have happened. And then the death is believed to be what in the United States is called SIDS, the Sudden Infant Death Syndrome. In British English, people talk about cot death. This is this occurrence of babies somehow falling asleep and then dying or lacks of oxygen in the first year of their life. There are various theories why this could be. Even though the medical profession has made a lot of progress in trying to analyze the reasons for SIDS, it's still sometimes a bit mysterious. Nowadays, parents get the advice that babies should sleep on their back, not on their tummy, so that this reduces the probability. They changed that a couple years ago. Let's hope that they are right this time. Now, about a year later, after Christopher dies, the second son, Harry, is born in November of 1997, and the next tragedy happens. The baby is found dead, Harry, in January of 1998. Again, the mom, Sally, is the last person to see the baby alive. Now the baby, it looks suspicious. 2 babies suddenly dead, and this baby shows some brain damage, and people are maybe from shaking the baby, maybe deliberately shaking the baby or something. Now, because of this suspicion, Sally and her husband Steve are arrested on double murder charges. So now some people think this can't happen. 2 babies die. The parents were just sick of the baby. Babies cry too much. They killed the babies. In particular, they go back to the report on the first baby and change ex post the diagnosis from natural causes, cot death, SIDS, to smothering. Maybe playing too hard, maybe deliberately, maybe pushing the baby too hard, or whatnot. Eventually, though, the charges against the husband are dropped. The mom is the main focus of the accusation now, because in both cases she was the last person who saw the baby alive, and now she's accused of murdering both babies. She flat out denies the charges. The husband continues to stand by his wife and to support the wife and says, no, my wife wouldn't do these things. In addition, they have a third baby born in 1999 during the proceedings. In court, there's a key argument by an expert witness who says the following. The 2 SIDS cases in the Clark family have a probability of 1 in 73 million. It's so unlikely that this happened, it must be 2 murders. So the expert witness very strongly makes a point that he believes the mom killed both babies. The jury is clearly impressed by the expert witness and votes 10-2 of guilt. And as a result, Sally receives a mandatory sentence of life imprisonment. So, let's have a good probabilistic look at the statements of the expert witness. How did he get this 1 in 73 million? He starts out, he says, I looked at the data, I looked at families like the Clarks, and he started out with a probability of a single SIDS case of being 1 in 8,573. Now that's by itself is nowadays considered a dubious estimate. There was in the past a lot of controversy about this. It's quite unclear what that correct number should be based on relative frequency data. For the sake of this discussion, let's keep the number as is. Personally, from what I read, this number is way too low. However, again, as I said, for the discussion of what comes next, let's believe this number. Then this expert witness said, oh, we had 2 SIDS in a row. So, let's assume independence. At this point, warning bells should go on in your head. But that's what this moron said. Let's assume independence. 1 in 8,573 times 1 in 8,573 is about 1 in 73 million. So, the probability of 2 SIDS in a row is 1 in 73 million. That's how he came up with the number that he gave in court. Then he said, oh, jury, you don't understand what that probability means. Let me illustrate it for you. We have about 700,000 births in the United Kingdom in a year. We should see this once in 100 years. That this happens accidentally. And then, and this really hit home in this country of sports fanatics, the UK, he said the probability of a double SIDS is as likely as you bet money on the 80-1 outsider at the biggest horse race that the country knows in a year, and you win 4 years in a row. And so these statements that the expert witness made to the jury apparently visibly impressed the jury and led ultimately to the 10-2 verdict or vote that then led to the verdict of guilt. Now, there are at least 2 terrible mistakes. and not even talking about the 8,573. The first terrible mistake was independence. Do we really believe that if this SIDS, about which we don't know much, happens to a poor family, that then afterwards that reveals no information whatsoever? So here's essentially the assumption of what the expert witness says. He said the probability of a SIDS on the first baby and SIDS on the second baby is just the product of SIDS on the first baby times SIDS on the second baby, and moreover, SIDS on the second baby is as likely as SIDS on the first baby. So those probabilities are the same. Do we really believe that's a reasonable assumption when it's a condition about which we don't know much, where there may be God knows what genetic factors that we haven't really explored yet, about a really mysterious nature? Shouldn't we look at, instead of conditional probabilities in empirical data, to estimate these numbers? No, he didn't do that. Later on, people did this, and they realized the conditional probability of a second SIDS case in a family after having a first one actually increases a lot over the unconditional probability. I found estimates, actually here I wrote as large as 1 in 200. Recently I found numbers as large as 1 in 100 or even 1 in 60. That means if a family has a SIDS case and then this couple has a second baby, for whatever reason, nowadays doctors think there may be genetic reasons, the probability is drastically increased, and these people have to be extremely careful. There is something like a genetic predisposition. So that means that this number of 1 in 73 million is way, way, way too small. The second probability is not 1 in 8,573. It's something much, much larger, and as a result, the product gets much larger. But things get worse. Here's our second terrible mistake. The prosecutor's fallacy strikes once again. Here's a brief summary of the prosecutor's family as a reminder for you from our previous lecture. These are exactly the cases we have. The damning evidence versus the innocence of Sally Clark. The expert witness said the following: given that Sally is innocent, there's a 1 in 73 million chance of 2 SIDS deaths in a row. But then came the prosecutor's fallacy. He said that means the probability of her being innocent is 1 in 73 million. No, in particular, of course, this being in the UK, there's a huge yellow press. Yeah, people then communicated there's a 1 in 73 million. This poor woman, Sally Clark, is innocent. Wrong. This all is a prosecutor's fallacy. We need the flipping formula. We need Bayes' rule to think about. What's really the probability of innocence? And this now then asks us, if we want to think about the various inputs that we need into Bayes' rule, what are the alternatives? If the woman is innocent, what are the alternatives? SIDS. If she's guilty, it's murder. What's the data on guilt, on double murder of 2 kids? That's also not so likely. Actually, people later looked at data, and SIDS is estimated to be 4 to 9 times more likely than double murder. So the calculation of Bayes' rule was never done in the trial, but people should have looked at probability of innocence, probability of guilt, and looked at murder versus SIDS. All this was never done, so the prosecutor's fallacy was never resolved. So to summarize, at least 2, some people argue 3 and more terrible mistakes were done. For the sake of our discussion here, 2 terrible mistakes: multiplying independent probabilities and the prosecutor's fallacy. Sally Clark or the husband appealed the case the verdict the first time in October 2000. the appeal was rejected. A second appeal in January of 2003 was successful and she was let go. There were at least 2 more women who on SID charges had been sent to prison. They were overturned and were let go. There was an ongoing trial where then the woman who also had lost actually 3 babies was allowed to go free. So this has huge implications in how SIDS cases were handled in the United Kingdom. Sadly, Sally really should have left prison much earlier. As early as October of 2001, the Royal Statistical Society of the United Kingdom made the statement that the 1 in 73 million figure has no statistical bias, and in their statement, in a press release, they very clearly pointed to the mistakes of the expert witness. You cannot assume independence, and clearly the jury had a case of the prosecutor's fallacy. So clearly there were these 2 terrible mistakes. Now, Sally goes free in 2003, but still the story ends sadly. Sally never recovered from the traumatic experience of losing 2 kids. She became dependent on alcohol and died of alcohol intoxication in 2007 at the age of 42. She's at the time survived by her husband and the 3rd son. The 3rd son lived happily ever after. No SIDS, no murder, nothing. So after all this, nowadays people believe Sally Clark was indeed innocent, and this was a terrible miscarriage of the court. There's a huge amount of information on this. The Sally Clark family has a website where you find much more information, in particular also on the probabilistic aspects. One of her lawyers wrote a book on the case, John Batt. And finally, for those of you who are interested in law, there's a lovely book called Math on Trial that looks at other mistakes related to math and probability and statistics in court. And so for those of you who love the law and perhaps are interested in studying this field, take a look at this book. To summarize, beware of prosecutor's fallacy. Do not multiply dependent probability very hard and focus on dependence versus independence. Because if you screw this up, tragedies may happen. This sums up our module on applications. I hope you had as much fun as I did on looking at the playful applications at the very beginning, the birthday problem and the Monty Hall problem. Then looking at the business applications, how in structured finance the problem of dependence versus independence led to many serious troubles. And then finally the terrible implications of prosecutors' fallacies has in court. Now in the next module we will move on to what's called discrete random variables, and we're going to look at metrics such as expected values, variances, standard deviations and other numbers. So please come back for the next module. Thank you. Welcome to our next module of an intuitive introduction to probability, decision making in an uncertain world. The title of our new module is Discrete Random Variables and Probability Distributions. So let's dive right in. The concept or the name of random variable often confuses people. What is a random variable? It's actually a very natural concept that I'm sure you have used before. So let's start with an example. Recall the experiment of rolling 2 fair dice. We had an example a while ago, and what are the possible basic outcomes? There are all the possible pairs between the number on the first die and the number on the second die. So 1, 1, 1, 2, all the way to 6, 6. We have these 36 pairs of 2 numbers, and they're all equally likely. Often, however, we're not really interested in the pair, but we're interested in the sum of the pair if we play a game. And so then, what do? We just add the 2 numbers. The 1, 1 then is the 2. The 1, 2 and the 2, 1 are the 3. We have seen this before. And so what we are doing actually, by building the sum, we give to each basic outcomes a numerical value. And voila, that's already a random variable. Here's a technical definition. A random variable assigns a single number, a single numerical value to every basic outcome. Now, unfortunately, I have to introduce just a little notation. I usually try to avoid notation because I don't want to confuse students with notation, but here we just need a tiny little bit of notation. Usually random variables need a name, and unless we have a very good name from the context of a business application or some other real-world application, we use capital letters X, Y, and Z. Now, a discrete random variable is a random variable where we only have finitely many possible values, or perhaps infinitely many values, but values I can count. But let's now, for the sake of this module, focus on a list of possible values. So, with the sum of two dice, the possible values would be 2, 3, 4, all the way to 12. Now, we want to talk about probabilities. Here, with a random variable, we call the collection of the probabilities a probability distribution. It gives a probability to every possible value that the random variable can take on. Again, a little notation. What's the probability? We write P of X. Some people like to write PR for probability of X. Some people like to write P of capital X equal X. That may look a little funny to you, but what that means is the probability that the random variable X takes on a specific value, and that's then denoted by little x. I don't care which notation you use, but if you look at textbooks, if you surf the internet, you will most likely find one of these four ways to write down a probability. The next step then is sometimes we sum probabilities, and that gets us to the concept of a cumulative probability distribution. What the heck is that? Now, if I think of the cumulative probability of a number of the random variable, I want to add all the probabilities for numbers less than or equal to the number at which I'm looking at. Sounds a little complicated. Here, the notation would be probability that the random variable capital X is small equal a particular value little x. Let's look at some example, and then I think it will be quickly get very clear. Back to our two dice. We had seen before the probability of a 2, that's just a pair 1, 1. There's only 1 out of 36 pairs that gives me a sum of 2, would be 1 in 36. 1 divided by 36. Then the probability that we roll a sum of 3 would, that's a couple 1, 2, or the other way around the couple 2, 1. So there are two possibilities out of 36. Probability 2, 36. And here you see a list all the way to the number 12. Now notice we cannot roll an 11.2. I cannot roll a pi, a 0, or minus 5. All those numbers have a probability 0. Now let's return to the cumulative probability. Here from a spreadsheet I put together a table that shows us first, in the first column, the 11 possible values that the sum can take, 2, 3, all the way to 12. In the next column, the individual probabilities, 1 in 36 for 2, 2 in 36 for 3, 6 in 36 for 7, the most likely value, and then it goes down again all the way to 1 in 36 for the number 12. Finally, in the last column, we have the cumulative probability. What is the cumulative probability, for example, of a 4? That's a probability that we get a 2 or a 3 or a 4. So you see, f of x, therefore 4 is 1, 6, 0.1666, and so on. That's actually the sum of the three individual probabilities. Here's an easy rule. For the largest number, the f of x is always a 1. In this case, the largest number possible is a 12. So for sure, with probability 1, we will roll a number of 12 or less. Now often people don't like these long Excel tables. They get too cumbersome, all these numbers, these many digits. So many people prefer a graphical representation of these probabilities. So here we have a graphical representation now of the individual probabilities. Again, we see all the numbers 2 to 12, and those are displayed here on the horizontal axis, the x-axis. On the vertical axis, on the y-axis, we see the level of the probabilities. You see the largest bar is at the number 7, and it goes all the way to 1/6, because the 7 is the most likely number when you roll 2 dice. You see then the nice symmetric form with the smallest probabilities for 2 and a 12. So these graphs of a probability distribution are very popular. Occasionally, you will also find graph of a cumulative distribution. Here, again, we go up in our numbers from 2 to 12, and we see that we get this type of step functions. That's very typical for the graph of a cumulative distribution of a discrete random variable. And we always see these steps as we hit the number 3, 4, 5, all the way to 12. Now, technically, I can also ask what's the probability I get a number of pi or smaller. Oh, I can look at this. Pi is between 3 and 4, so the bar in the graph shows me what the cumulative probability of that number is. Any number smaller than the smallest number possible, the 2, has a cumulative probability of a 0, and anything 12 or larger gets the number 1. Now, let me show you a different example that many of you may be familiar with, and that's the game of roulette. So what in roulette happens is that there is a little ball that rolls around the wheel and eventually falls into a so-called pocket. Every pocket is connected to a particular number. Here in the picture I have a wheel as it's used in Europe with 37 possible numbers. There's a 0 and the numbers 1 through 36. In the United States, for example in Las Vegas, there are actually 38 pockets. There's a 0 and a double 0. Now let's take this game of roulette and sort of describe it in the words of probability. Here we have a random variable, the possible values. Here I call the random variable R for roulette, and it has the possible values 0, 1, 2, all the way to 36. All numbers are equally likely. Quick aside, I know some pros may say, oh, the croupier may actually be able to game the ball a little bit and speed it up a little faster or a little more slowly to aim for a particular pocket. We don't think of that. We assume an absolutely fair game. That's a little side for the pros among you. So here now we assume that all 37 numbers are equally likely. This probability distribution is also called the uniform distribution. Here I wrote it down for you. We get the numbers from 0 to 1, 2, all the way to 36, and they all have a probability 1 divided by 37. Remember, the 37th number is 0. And now here we have a graphical representation of it. All numbers are equally likely. This graph looks pretty boring to me. It also gets convoluted. We have now 37 of these bars. So in the next lecture of this module, we actually want to go beyond these graphical representations. Maybe they're pretty pictures, but they're not always all that useful for us humans with our bounded mind to really grasp the uncertainty. And that will be the next step. So let me wrap up this first lecture of the new module. We learned about the concept of a discrete random variable. We then introduced the concept of a probability distribution, which really is nothing new. It's just a little bit of new terminology, giving probabilities to the numbers of a random variable. And we discussed the representation either in tables and graphs. Thanks for being with us at this lecture, and please come back for the next lecture. Thank you. Welcome back to the second lecture of probability distributions. Now we're going to talk about the expected value. Why do we even need this number? I had shown you before the graphical representations of probability distributions. As soon as we have more and more possible numbers in a random variable, these graphical representations get messy. It's difficult for us humans with our limited brain capacity to really grasp and understand these random variables. So what we like to do is summarize the information into some so-called summary measures. And the first such measure is the so-called average, mean, or expected value. Let me show you the definition. First time you look at this definition, you think, what the heck are they thinking? The mean or expected value is a probability weighted sum of all possible values. Here's the formula. The expected value e of x, or also called mu, the Greek letter for the m, mean, mu, is equal to x1 times the probability of x1 plus x2 times the probability of x2, blah blah blah, plus xk, the last value, times its probability. The first time you look at this formula, you say, why this looks so complicated? But let me assure you, this is something you have done before, and this is actually very natural. And it's a natural extension of things we do all the time when we average out numbers. Let me show this to you in a spreadsheet where we're going to look at the really simple example, the fair die. So let's have a look at this spreadsheet. Now that we have understood the formula and seen the formula in action, let's talk about the interpretation. Many people find the interpretation of an expected value of 3.5 really strange. Because when in everyday language, when we use expectation, I expect something to happen, then I think there's a very high probability something will happen. But the probability of a 3.5 is 0. So here we have a clash between the everyday language we use when we use the term I expect to meet someone, I expect it to rain, I expect to see something, and the concept of expected value. So how can we understand this idea of expected value, mean, average? That is best explained using a Monte Carlo simulation. Here I prepared such a Monte Carlo simulation of a fair die for you. Let's look here at this spreadsheet. I have 10 columns of 1,000 numbers each. So here I have 10,000 times essentially a fair die that's rolled. Then I average out with the everyday gut feeling number, add up the 10,000 numbers and the sum divided by 10,000, and here's what I get. In this particular example of 10,000 random numbers, we have an average of 3.4843. Ha! That's very close to now the 3.5. And this gives us now the key to understanding an expected value, a mean, an average. It does not mean that on the next roll of a fair die I will get a 3.5. That's impossible. But what this number means is that if I repeat this experiment of rolling a fair die many times, then the long run average will get close to 3.5. And that's the key interpretation here. I ask you to play around with the spreadsheet, which you can download. Click F9, refresh the numbers, and you will see the means fluctuate, but they fluctuate very closely around 3.5. And this will give you some feeling, hopefully some intuition for the concept of expected value, mean, or average. So let's go back to the slides, summarize what we learned about an expected value of a fair die, and move on to some more examples. Here's a summary of what we just did in the spreadsheet. The expected value of a fair die, our random variable d, is 3.5, and we would now call this either the mean, the average, or the expected value. Let's now look at another example. Back to the roulette game. Recall there are 37 numbers. Actually, these numbers are now also color-coded. 0 is special, gets the color green. In addition, we separate the other 36 numbers into 18 red numbers and 18 black numbers. And here in the picture of a roulette table, you can see the colors of the various numbers. And now it's actually possible for you, not just in this game, to bet a chip on a particular number, but no, you can also bet on a color. So let's now say you want to bet on the color red. What this means is that if one of the 18 numbers that are color coded red appear, you win an extra chip and you get 2 chips back for a net win of 1. If, however, the green 0 or one of the 18 black numbers appears, then you lose your chip. Question: what is the expected value of this color bet? How much money will you win or lose on average? So let's take this game into our language of probability. Here we have a random variable, b, for your bet, and there are 2 possible values. You win 1 or you lose 1. -1 for the loss. The probability of you winning is 18 divided by 37. Why? Because there are 18 red numbers out of 37. So you see the probability is 48.65%. The probability that b takes on the value -1, that means you lose your chip, is 19 divided by 37. Why 19? 18 black numbers plus 1 green numbers, you lose. So 19 divided by 37 is the probability you're losing. That is 51.35%. Now we can, with these probabilities in hand, we can calculate the expected bet value. So E of B is 1 times the probability of a 1, 18 divided by 37, plus -1 times the probability 19 divided by 37. In the end, it comes out to a loss of 0.027. So, on average, you will lose money with this bet. Let's think back to the interpretation we had with the die. If you play this color bet for a long time, many times in a visit to a casino, on average, you will lose about 0.027 chips. In the language of gambling, what this means is the so-called house advantage. On average, the casino wins money. Now, I understand some people don't care much about gambling. Let's now look at a real-life application where the expected value is really important. Recently, I was on a business trip and I had to rent a car. And with the car rental, I was told that my insurance, in case I have an accident, carries a deductible of 800 euros. That means if I have an accident, the first 800 euros of damage I have to pay. Any damage above that is paid for by an insurance. Then I was offered the following extra insurance. For an extra fee of 84 euros, I could buy a deductible of 100 euros. So I could decrease my deductible by 700 euros. Here was my decision problem. Should I buy this insurance? So let's translate this real world problem into a probability problem. There's a random variable, which is my accident payment. Let's make a simplifying assumption. As soon as there's an accident, the damage exceeds 800, so I will certainly have to pay 800 in that case. So we neglect accidents like bumper damage of, say, perhaps 500 euros. So we either I have to pay 800 euros or 0 because I have no accident. If I buy the extra insurance, these numbers would be 100 and 0. So, what's now the larger cost for me? Here, let's look at the expected value. What is the expected value of my payment without insurance and the extra insurance? And what's the expected payment with the extra insurance? So, now I have a problem. I don't know the probability of an accident. So, let's call that P for the moment. Without the extra insurance, with probability P, I have to pay 800 euros. With the probability 1 minus p, I pay nothing, no accident. We only have the two outcomes, accident, no accident. With the extra insurance, I have to pay 84 euros right away. Then with probability p, I have to pay a deductible of 100. With probability of 1 minus p, I pay nothing. And so in this case, as you here see on the slide, the total payment would be 100 times p plus 84, the expected value of the payment. Now, some of you may think right away, oh, now I can ask, at which probability would these two expected payments be the same? With a little bit of algebra, we get to 8 1/3%. So, if I think that my probability of an accident is larger than 8 1/3%, I should buy this insurance. If I think the probability of an accident is smaller, I should not buy the insurance. But I don't know the probability. Ha! But now let's think about the insurance company. They are not forced to offer me this extra insurance. They are willing, freely willing to give me that insurance. In fact, the car rental agents try to talk me into buying that insurance. So what does that tell me? Obviously, it's profitable for them to buy me to sell me this insurance, for me to buy it. So clearly, they have data and they know the probability of an accident is less than 8 1/3%. Let's think about this. In 1 in 12 car rentals, do I have an accident? Let me knock on wood. I hope not. I don't think I have that high of a rate. So, therefore, my conclusion was, I believe the car rental agency thinks they will make money on this extra insurance, so they must think the probability of an accident is actually very, very low, and they're happy to take the 84 euros from me. So in the end, I decided not to buy the insurance, and luckily I didn't have an accident and returned the car without any damage. And so this sort of summarizes or concludes the real-world application of an expected value. So, to summarize, we learned about our first summary measure, the expected value, the mean, the average. We saw in the spreadsheet the interpretation as a long-run average of many repetitions. And in the end, we saw a real-world application, namely this tiny insurance application. Thanks for your attention, and please come back for more in the next lecture. Thank you. Welcome back to an intuitive introduction to probability, decision making in an uncertain world. In the last lecture, we learned about the concept of an expected value. We introduced the expected value as a summary measure because the graphical representation or the table representations of probability distributions can quickly get overwhelming for our limited brain, our limited human mind. And so we like to aggregate all this information, the possible values, the possible probabilities, into a single number. But there's a drawback. In the aggregation, we lose a ton of information. The number 3.5 on the fair die doesn't give me any indication about the variation in the actual numbers. I can't communicate with a 3.5. Oh, there's actually variation. The 3.5 doesn't actually show up. So here, as I show in this graph, in the probability distribution, I have these 6 bars. I see, I have 6 different numbers. There's uncertainty. There's only a 1 in 6 chance of them coming. But the 3.5 doesn't give me any of that information. So I lost a lot of valuable information. Now look at these 4 graphs. I created here 4 very different probability distributions that all have one thing in common. The expected value is always 3.5. In the upper left-hand corner is our fair die. In the upper right-hand corner, I have the probability distribution for a die with 3 1s and 3 6s. But I can only roll 1s and 6s, but the long-time average is 3.5. The bottom left-hand corner, I have 3 3s and 3 4s, so I have a 50-50 between a 3 and a 4. Again, the average is 3.5, but all the numbers I see are just 3s and 4s, much less variation. They're very close to the 3.5 as opposed to the 1 and 6. in the upper right hand corner. And in the bottom right hand corner, I have a really funny die. It has the possibilities of -5, -2, 9 and 12. All of a sudden I may have negative numbers or double-digit numbers. Again, the average is 3.5, but I have way more dispersion, way more variation. And that's a big minus. In the 3.5, or in general, the mean, the average, the expected value does not give us any information about variation. But in many business applications, that variation is important. Sam Savage of Stanford University coins a beautiful phrase, the flaw of averages. It's a game on words, not the law, the flaw of averages, that people rely too much on averages and ignore variation. And here I also have a beautiful quote by the late historian and evolutionary biologist Stephen Gould, who says our culture encodes a strong bias either to neglect or ignore variation, and that's dangerous and can lead to trouble. So this problem with expected value now motivates us to go a step further. We need a measure for variation. So let's think about this. How could we define a measure of variation? Here's the easiest thing you could think of. Let's take just the average deviation, the probability weighted sum of the possible deviations. So take the difference x1 minus mu, that's the deviation, times its probability. And then take x minus 2 times its probability, and so on, and add up all those numbers. Wouldn't that be a beautiful measure? It sure would, but it doesn't work. I have bad news, and this is, in fact, I made it a theorem here. I represent it as a theorem. This concept, this idea of an average deviation does not work because it's always zero. This is actually a way to think of mu. Mu is exactly at the position that the negative deviations and the positive deviations add up, average out to zero. So the simplest idea does not work. Why doesn't it work? If you take a look at this spreadsheet with a fair die, it doesn't work because the minus and plus deviations cancel. So at this point, my students always say, oh, I have an easy solution. Cut off the minus sign. Use the absolute value. And indeed, this is something that's possible. It's called MAD, M-A-D, the mean absolute deviation. So here we average out the absolute differences. This is possible, but it's rarely done in practice. And the reason is the absolute value function isn't as easy as it looks. It has a kink at zero. Here I have a graph of the absolute value function for you. And in the language of mathematics, it has a non-differentiability at zero, which later on creates some problems. So while this concept may be intuitive, it's not as easy as it looks like. And therefore, let's not use it. What's the next easiest concept to get rid of a minus sign? Squaring the numbers. And that's what we do. And this leads us to the concept of a variance. A variance is a probability weighted sum of the squared deviation. So now a deviation of -2 gives us a +4 squared deviation, just like a deviation of a +2 gives us a +4 squared deviation. So no more a cancelling of negatives and positives. Here is a proper definition. If our random variable has possible values x1, x2, all the way to xk, it's a probability weighted average of the squared deviation. We write VAR for variance of x. Sometimes you will also see the notation sigma squared. In the spreadsheet for fair die, I calculate the variance of a fair die for you. It's 2.91667. Now, however, it's necessary for us to go a step further. The variance has a big disadvantage. We square the numbers, and then we get squared units in applications. In our business or real life applications of probability, our random variables often have units. Remember back to the example I showed you with the euros in the insurance example. There, squared deviations then would be euro squared. But what the heck are euro squares? I don't know what euro squared are. So we want to go back from euro squared to euros. How do you do this? With the square root. Bingo. And that's the last concept we need. We take the square root of the variance to obtain the concept of a standard deviation. That's why we have the sigma. Sigma is a standard deviation, the Greek letter S for standard deviation. The proper definition is the standard deviation is a measure based on the variance for the average deviations of the values of a random variable around its mean. Here for fair die you can quickly calculate the number 1.7. To sum up this lecture, we learned about the flaw of averages. Don't just look at means, at averages. There's too much information loss. We need to also measure the variation. And our preferred summary measures for variation, or in economics and finance, people like to talk about volatility, are the concepts variance and standard deviation. I encourage you to play around with the spreadsheets so you get some feeling on how to calculate these numbers so we can use them in some future lectures. Thank you very much, and please come back for more on an intuitive introduction of probability. Thank you. Welcome back to an intuitive introduction to probability, decision making in an uncertain world. Now, in this lecture, I want to show you an example of an application of means, variances, and standard deviations. One area where random variables are heavily used is in the area of finance. When finance practitioners and academics talk about financial models, essentially they are talking about random variables. And they then use these random variables or these economic models to forecast, because they need forecasts to handle economic or financial risks. And that's what this is all about. Again, they have complicated probability distributions that are too difficult to understand, and so they like to summarize these numbers in these summary measures that we have seen before. Let's start with an example here. Here we have a model of an investment fund. We have 6 different return scenarios. In the next quarter, we may lose 15% of our money, or we may lose 7.5% of our money, blah, 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 or we make all the way to 14% of our money. In an Excel spreadsheet that comes with the course, you can see all these numbers and the calculated cumulative probabilities. These probabilities that we see here on the returns, they are actually empirical probabilities. Thinking back to module 1 of this course, probabilities we are using here, probability concept number 2. Based on historical values, you think these are reasonable probabilities. With 2%, you lose 15%. With 5% probability, you lose 7.5%, and you believe there's a 20% chance that you make a lot of money, a 14% return. And then in the last column, we see the cumulative probability. Now, many investors who want to invest, they don't want to look at 6 numbers and these probabilities. They are interested in some metrics. And now, the first metric people can look at is exactly our expected value. So here we have the expected value. Let's think of this fund that someone wants to invest in as a random variable. Here we have the simplified random variable where we have 6 possible values. We can calculate the expected return. Remember how this goes. You take the first value, multiply it with its probability. Take the second value, multiply it with probability, do that for all values, and then sum up all these products, and voila! Here we get a number of 4.95. So this would now say that according to this model, the expected return, that's our units here, the expected return of this investment fund is 4.95%. But now danger! There's no sign of risk. It says, oh, the average value is 4.95%. Does that mean that I will make 4.95%? No! Remember the interpretation. This would only be true if this model is correct over a long investment horizon. Many quarters of investment. But we're only thinking about 1 quarter now. So here we have again the problem of the information loss in the expected value. We need now to model the volatility, as they say in finance, or we use the terms variance and standard deviation. So let's calculate the variance. Remember the variance, all the deviations squared times the probability of these deviations. Here I quickly calculated it for you, and we get a variance of this return of 43.8975. And now comes the killer, percentage squared. Why do we have these funny units? Yeah, look at the formula. We have minus 15%, minus 4.9%. That difference of 19.95% gets squared. And now we get these squared units. But they don't mean anything to anyone. Therefore, we now need an extra step. We take the square root of the variance to obtain the standard deviation, 6.63%. And this is now our measure for the volatility, some people go further, for the riskiness of this investment. They say the standard deviation of this fund's return is about 6.63%. Because we took the square root, we went back to regular units, the percent. And as I said, this standard deviation is a popular measure in economics and finance of the concept of volatility. How volatile is this investment? So here now you saw a nice real-world business application on expected value, variance, and standard deviation with an application to an investment fund. Welcome back to an intuitive introduction to probability, decision making in an uncertain world. The topic of this lecture is the binomial distribution, which is perhaps the most widely used probability distribution that has discrete outcomes. Here there's a long list of applications. It's used in medicine, in statistics, in marketing when we look at customer behavior. I will show you this later. In manufacturing, in quality management. And in the next lecture I will show you a cool example from airline overbooking in the airline industry. So let's go straight to the binomial distribution. We are looking now first at a random variable that has only 2 possible outcomes. We call them success and failure. Just the number 1 for success, number 0 for failure. Just those 2 outcomes. A half isn't possible, 2, 3, 4, 5 are not possible. The probability of a success is little p. The probability of the failure, then by the complement rule, is 1 minus p. This random variable, the simple random variable, is called the Bernoulli random variable, and this distribution, the Bernoulli probability distribution. We can easily calculate the expected value and the variance for this random variable, and here I quickly have those formulas for you. Now, this is pretty boring. Where it gets interesting is now when we repeat a Bernoulli random variable over and over again. This is now called Bernoulli trials. So we have a sequence of identical trials. Each and every time it's a 0 for failure, a 1 for success, a probability p for success, 1 minus p for failure. And all the individual trials are independent. So what we now essentially do here, we don't just have one Bernoulli random variable, we have a whole sum of random variables, and they are all independent and identically distributed. People in probability theory often use the abbreviation IID for independent and identically distributed. And this particular distribution is now the binomial distribution. It depends on 2 parameters. On little n, how many repetitions of the trial do I have, and the probability little p of the success. Now, we can quickly calculate the mean and the variance of this binomial random variable. Here, just to scare you a little bit, I showed you the proofs. The only thing that's important, but it's very intuitive, as you will see in applications, the expected value is n times b. P is the number of trials times the probability of a success. So that's enough abstract nonsense. Let's look at now some examples. Let's say you flip a coin and you call a head a success and tail a failure. And now let's say you flip the coin 5 times, and the question is now, how many times do we get a success, a head? Now notice, this is easy if I ask you about 0 heads and 5 tails. That would mean we get a tail on the first try, and on the second, blah blah blah, and on the last. Because they're independent, remember now the multiplication rule for independent events. The probability of 0 heads and 5 tails means we get a tail and a tail and a tail and a tail and a tail. We multiply a half times a half times a half times a half times a half. A half to the power of 5 is 1 in 32nd, is a tad more than 3%. Now that's easy. We learned that before. We can do this with our previous formulas. But now it gets tricky if we don't look at a special case of 0 heads, but of 1 head. Why is this now difficult? Ha! If I have 5 flips of a coin and 1 head, that head could be the first coin, and then I have 4 tails. But it could also be that I first flip a tail, then a head, and then 3 tails. Or I do 2 tails, a head, and 2 tails. And now you see, oh, this adds up. Suddenly there are 5 different possibilities. The head could be in the first position, or in the second, or in the third, or in the fourth, or the fifth. Now, I have to look at all these possible outcomes and then start adding the probabilities. You can see this gets quickly messy. Now here you say, oh, I can see there are 5 possibilities because there are 5 positions, and each of them has a probability 1 in 32, so I can add this up. So maybe this we can still handle in our head. But I can tell you, as soon as n gets a little larger, or as we look at 2 successes out of n, things get awfully nasty. Luckily, there's now an easy solution, namely in Excel there's a function called binom dist that calculates these numbers exactly for us. Let me show you where you can find this function in Excel. Here, please have a look at the spreadsheet for the probabilities of 5 coin flips. Before I explain all these numbers to you, please follow me here in Excel. Under formulas, you find in this leftmost icon, insert function. And after insert function, there is statistical, a collection of functions from probability and statistic. And under statistical, you find the function binom.dist. If you have an older version of Excel, the period sign, the dot may be missing, but don't despair, everything will work on your computer as well. And when you click on binom.dist, this interface, this function appears here, and we can either via a dialog box or by typing fill in the numbers that we need. And this is what I have already done here. So let me now show you what this actually looks like. So here now we go here. What have I typed here or got in via the insert function? We have first an equal sign because I want to do some math. Then binom.dist, and now I need to enter 4 numbers. The first number I need to enter is the number of successes. Here I typed A4 because I want to refer to the cell A4 where we have the 0. Next comes little n, the number of repeated Bernoulli trials. Here I said we flip the coin 5 times, so this number is a 5. Next number is a 0.5. Why? That's the probability of a success, 0.5. And finally, here I want to calculate the probability of exactly a 0, and this last argument therefore needs to be the number 0 or the word false. This is just a technicality, there's nothing to be understood here, just accept it as a false. Now here on my screen in Switzerland it shows semicolons. This is in the Excel that we have here in Switzerland. In other countries this may be a comma. So keep that in mind. If you type this and you get an error message, depending on your country, this may need to be a comma instead of a semicolon. So now let's go further down here. Let's look at when I have y equals 2. If I click here, we see binom.dist of the 2, that's in A6, n is 5, 0.5 is a probability, and false. And that's how I very easily get the probabilities of having exactly y successes, where y could be any number 0 to 5, when I flip a fair coin. Now remember the cumulative distribution. I can also immediately calculate those probabilities. Here, for example, for a 2. I type exactly the same first 3 arguments as before. So I have binom dist of here cell A6, where I have the number 2. Still 5 trials, still a probability of 0.5. But for the cumulative distribution, the last argument always must be the number 1 or a true. And so here now, the probability that I have 0, 1 or 2 heads, successes, is exactly a half. And as always, for the largest number, of course, the cumulative probability has to be equal to 1. So, in a nutshell, by typing in binom dist with 4 arguments, you can very quickly calculate any binomial distribution probability that you may care about. You can calculate probabilities of hitting y exactly or of cumulative probabilities, and you only need to plug in little n, the number of Bernoulli trials, and the probability. So let me summarize all these numbers now in the slides for you. So on the next 2 slides I summarize what we just learned in Excel. So here on this slides with the 5 coin flips, I show you the commands that you need to type in order to calculate the probability of, for example, having y equal 2 heads out of 5 coin flips. So we have all the different probabilities, the binom dist function, and recall that we want to use the last argument of false when we look at the probability of an exact number of coin flips. At the bottom we can also see the expected value and the variance quickly calculated using the specialized formulas that we saw before for binomial probability distribution. Next, we also saw the concept of the cumulative distribution. That's when the last argument in Excel is a true. That's again adding up all the probabilities up to a specific value. And so here I've summarized those numbers for you. Now, as I said at the beginning, this probability distribution is used in neat applications. And so let's get away from this little toy problem to a really cool application. Some advertising stunt that a beer brewing company in the United States pulled in the 1981 Super Bowl. The Schlitz Brewing Company asked at the time, live on TV, so this wasn't televised in a film studio before and then shown. So this was not canned, it was live on TV. They asked 100 beer drinkers who had proclaimed, my favorite beer is one of your competitors, this beer brand called Michelob, and asked them in a blind taste test between their beer Schlitz and the Michelob beer, which beer do you like better? Now at first when you think that, this is a god-awful idea. What are they doing? Aren't they nuts? You ask these people who say this is my favorite beer to test it against your beer. Isn't it likely that you look like an idiot and 100 people will say, no, my beer is still my favorite beer, or maybe 98 say it's still better, maybe you convince 1 or 2. Is this really risky? So let's now take this advertising stunt and put it into a probability framework. From Schlitz's view, there are two outcomes, a success and a failure. What's a success? A success is that one of these beer drinkers says, Schlitz is my favorite beer. Failure, someone says, oh no, I stay with my favorite beer, Michelob. But now keep in mind, these are American beers. And they're not some special American microbrewed beer. No, this is some large beer companies. And let's taste it. These beers are all rather similar in taste. Some people may even question whether they have any taste at all. But I don't want to discuss this here with my American friends. So let's assume now it's essentially impossible to distinguish between these two beers because they are taste alike. Ha! Now we get into a binomial distribution context. We have success, probability a half. Failure, probability a half. We have 100 people sitting in the room. They're not talking to each other. And anyway, they are blind. This is a blind tasting. It doesn't say on the bottle whether it's Michelob or Schlitz. So we really have a binomial setup. And now we can analyze this advertising stunt using the binomial distribution. Question. Let's say a really bad outcome for Schlitz is that less than 1/3 of all people favor their beer. What is the probability that that happens? The probability of less than a third of 100, that means that the number of successes is less than 33 1/3, means the number is, given that we only have integers, y is smaller equal 33, quickly calculated with binom dist is 0.044%. So it's tiny. So it's really unlikely that we look so bad, if we are Schlitz, look so bad with this ad. What's the probability of a pretty good outcome? Let's say a pretty good outcome is 45 or more. Why is that a pretty good outcome? I think it's a pretty good outcome because these are all people who say Michelob is my favorite beer. If we can get 45 of them to suddenly prefer us, that's pretty impressive, wouldn't you say? And look at the probability. More than 86% chance that in this blind test this will happen. Here I calculated some other probabilities for you. If you consider less than 40 bad, less than 2% chance of that happening. The probability of hitting exactly 50 is almost 8%. The probability of 50 or higher is 54%. So there's more than half a chance that 50 or more people will favor your beer. Of course, under the assumptions, which I think are realistic, that you can't really distinguish the taste. So, in the end, it looks like this advertising stunt isn't all that risky. So now, of course, you're curious, right? What really happened that day in 1981? Exactly 50 out of the 100 loyal Michelob beer drinkers favored Schlitz beer. So they got exactly the expected value, what a coincidence, under their model. So to sum up, the advertising stunt wasn't all that risky, and it turned out it was a nice advertisement. Quick aside for people around the world, in the United States you're allowed to do what's called comparative advertising. Here in Switzerland, for example, it's not allowed. I can't say on TV, your product is bad, my product is better. I can only say my product is good. So just as an explanation for those of you who are surprised about this comparative advertising, it is allowed in the US. And this brings me already to the end of this lecture. We learned about a very important discrete probability distribution, the binomial distribution. It can actually get quite tricky if you look at the math underneath it. You don't need to do this because we have a beautiful Excel formula, binom.dist, which makes the calculation of probabilities very easy. And we saw a really cool, cute application of it in a legendary TV commercial from the United States. Thanks, and come back for another really cool application of the binomial distribution. Thank you. Welcome to our last lecture of this module on discrete random variables and probability distribution. In this last lecture, I want to talk about a very important application of the binomial distribution and probabilistic thinking in general. Airlines. Airlines overbook their flights, which means, let's say there's a flight from Zurich to London that has 200 seats. Airlines may actually sell 210 tickets or 220 tickets. Why are they doing it? What are the benefits and the costs of doing this? Airlines face a big problem: last minute cancellations or total no-shows. People may cancel a flight just a couple hours before it's supposed to take off, and they still may get a substantial refund. At this point, the aircraft may leave with empty seats. That's bad for the airlines because there's lost revenue. They could have sold a seat, they could have made more money. And as we know, airlines are in a tough competition, tough business. They really need that money. It is also said that airline seats are the most perishable consumption good that exists. If you think about tomatoes in your fridge, they decay over time. They first get wrinkles and eventually they get moldy and you have to toss them away. It's a process. Not so with airline seats. An airline seat is fresh, meaning you can buy it until 5 minutes before the departure. The door closes and it's dead. It decays from 1 second to the next. It was available for sale and it's gone, and the airline cannot sell it anymore. It went bad. It went moldy, sort of in an instant. And that's very bad. So the airlines want to get extra revenues, and one way is to do airline overbooking. That's the benefit. The cost, on the other hand, is now when too many people show up. You have only 200 seats, you sold 210 tickets, suddenly 205 people show up. Now you have to buy some people out of traveling, either by giving them vouchers, or in the worst case, if you don't have enough volunteers who take vouchers, you have to kick off people. That costs you money directly. You may really annoy your customers and they say, I never fly with that airline again. So you may have serious loss in customer goodwill, and that's difficult to put a Swiss franc or dollar figure on that. And in general, you have customer dissatisfaction. So the question now is, what's the best behavior of airlines, and how can we understand their decisions? So we want to look at how do they trade off the benefits on potentially more revenue against the cost of disgruntled customers and giving out vouchers, or perhaps have to pay for hotel nights for customers. This is actually an example of a very large and an important area in what business schools call operations management, and this is the area of revenue management, how to increase revenues. Now, for the sake of this discussion, we make a simplifying assumption. All people make the decision of whether to show up or not at the airplane independently with the same probability P. This independence, of course, is not quite correct whenever you have groups traveling. A family of 4, parents with their kids, maybe all go to a vacation trip, visiting relatives, or nobody goes. So clearly there is some dependence. Or some business people either all go to visit a customer or nobody goes. Here we simplify from this and say all people make the decision independently with a probability P. And voila, we're in a binomial setup and we can use the binomial distribution. I put together a large spreadsheet for you on airline overbooking. So let's have a look at this spreadsheet. Here, with a yellow background, I provided some parameters that we just take as given. We have an airliner with 200 seats. The price of a ticket is $300. The bump cost is $500, which means in addition to reimbursing an overbooked passenger who cannot fly with us, the $300 for the price, there is also a $500 voucher or hotel cost, or you name it. And we assume a probability of no-shows of 0.07. I found this type of number in some reports on airline overbooking. Here now is the number of tickets sold. Let's say we sell 200 tickets. Now look at this. Under the assumption that 7% don't show up, we assume 14 people won't show up. So on average, only 186 people show up. So on average, our airliner is not full. We don't like this. And we see here that revenues would be in this case 55,800. Now let's say we sell 205 tickets. Now the expected value of people showing up is still nowhere close to 200. It's now 190.65. Notice the expected revenue went up. How did I calculate those? Now let's go deep into the spreadsheet here. If we sell 205 tickets, then in the worst case, 205 people show up. My revenue, however, is only 60,000. Why? Because only 200 people will actually leave with us. 200 times 300. Then I have the overcost of 2,500. That means 5 people get overcost of 500. 5 people get 500 each, 2,500 in addition to the 300 that I don't get. Makes revenue minus cost 57,500. Now how likely is it that that happens? Yeah, look at this probability. It's a binomial distribution of having exactly 200 people show up. If I sell 205 people show up, if I sell 205 tickets with a probability of 93% showing up, that's essentially 0. This worst case scenario just doesn't happen. Let's look at now this case, 202 people show up. Again, the revenue is the same, 60,000. I can only take 60,000, make only that because I can take only 200 with me. 2 people I have to bump, that's 500 in overage cost. So I make net only 59,000, not 60,000, only 59,000. What's the probability of that happening? Still very tiny. And again, I use a binomial distribution. 202 people show up. If I sell 205 tickets with a probability of showing up of 93%. That's 1 minus the 7%. And so now I have all the possible revenue minus cost. Here I have all the possible probabilities. And then I can calculate the expected value, which I do here in the column J. I add up all these numbers. Now I can tell you the truth, I don't actually do this for all the possible numbers. Why? Because at some point they're all 0. The probabilities are so tiny. And here I get the rounded number to 2 digits, 57,193. Now let's play with this. Let's say we sell 5 more tickets, 210. What happens to revenue minus cost? It still goes up. Let's try 214. It still goes up. Now let's go crazy. 230. Not a good idea. It goes way down. Why? Because suddenly it's very likely that we have to bump many people. For example, if we sell now 230 tickets, the probability of, say, 214 showing up is 10%. That's rather high. So clearly it's not a good idea to sell 230 tickets. Now, how can we find the optimal number? Here, with some trial and error, you can play around with this number, and it's around 214 or 215 is the optimal number. Now, for those of you who know a little bit more Excel, if you have access to the Excel solver, I have hooked up an Excel solver to this Excel sheet, and with this solver we can actually find the optimal solution here. However, that requires some optimization, which is not part of this class. But for any people who have played around with the solver before, you may find that interesting. Now, let me summarize what we have seen here in the slides. And move back to the slides. So, let me summarize what we just learned. the objective of the airline overbooking problem is to find the optimal trade-off between the benefit of selling more tickets than you have seats on an airplane and the cost of perhaps having to push off customers from the airplane who had booked a regular ticket. And in the spreadsheet, we saw how we can use probabilities to sort of find the optimal, the maximized expected payoff to the airline. Now, clearly, some assumptions went into our calculation, but I think there's one very robust takeaway. It is not optimal for airlines to only sell as many tickets as they have seats. It really is necessary for them to overbook their flights. To summarize, we have now seen in our last lecture in this module an application of the binomial distribution, namely airline overbooking, which is just one example of this large area called revenue management. And this concludes the module on discrete random variables and discrete probability distributions. In our next module now, we will take a look at continuous distributions. We will see the famous bell curve and the normal distribution with some cool applications. So, please stay with us and come back for the next module of an intuitive introduction to probability, decision making in an uncertain world. Thank you.
Hello and welcome to the third module. Today we are going to travel together to the Swiss village called Sanidorf. Sanidorf is a small village by a Swiss lake inhabited by 16 men and women. Well, obviously these 16 men and women are different in their height. Some are bigger, some are smaller. Another difference of the inhabitant of this village is the amount of money that they have in their bank account. Some of them are very rich, some of them have just very little money. So today we're going to take data about the height and wealth of the inhabitants of Sanidorf and learn a little bit more about random variables. If we go to our table here on the right of our document, we have the information about the height and the wealth of the inhabitants in Sanidorf. We have an inhabitant ID for each of those, and additionally we have some data here about the wealth in US dollars of these inhabitants after winning the lottery. This is something that we will use for a later question. So as we see, we have different heights for different inhabitants and different amounts of money in the bank account. Some have very few, some have very much. Now let's use the information to answer some questions. The first question asks us to compute the arithmetic mean of the height and the wealth of the population. Well, in Excel we can calculate the arithmetic mean by using the formula average, as we see here. If we want to calculate the average in the height, we would just take the command average here and select the corresponding column in the data that I just shown. If we would like to do this with the wealth, we would do exactly the same command, just average, but instead of using the column K4 to K23 in Excel, we would move to the column L4 to L23, where we have the data about the wealth. This would be the results. Now we have an extra question. Compute the standard deviation and variance in height and wealth for the population in Sanidorf. Well, to calculate the standard deviation and the variance, we can use these formulas. STDEV.P or .S for the standard deviation. The only difference in these two formulas is that we would use the one with .P if in our data we would have the whole population, which is the case now. We have the whole population of the village. If we would only have one sample, meaning some inhabitants of the village, we would use the same formula but with .S for sample. Similarly, we would calculate the variance for the population with .P and the variance for the sample with .S. So if we apply the formula here, STDEV.P for the same data, meaning for the height in the inhabitants, we would have a standard deviation of 13.003 for the height and a standard deviation of 120 million, or no, 12,078,299 for the wealth. So as we see, the standard deviation in the height is much smaller than the standard deviation in the weight. Similarly, we would get the results for the variance, which as well differ very much in the absolute value. The new question is an interpretation question in which we will use the standard deviation and the variance that we just calculated. And the question is, if a new inhabitant was about to move to Sunnydorf and you would have to make a guess about her height and wealth, for which of both variables would you think that your error, measured in the units of each variable, would be smaller? Well, here we know that the intuition about the standard deviation is that if the standard deviation is small, then the values are much more concentrated around the mean. This is what we see in the case of the height. And this is also a logical thing. The height of a man or a woman is constrained between a much smaller values than the wealth of a man or a woman. So if we would do a prediction about the height and the wealth of a new inhabitant, we would probably do a much smaller error in predicting the height, although we would have in principle no idea about the height of this person, than in predicting the wealth, due to these differences in the standard deviation. Now we can play a little bit with our data to answer another question. Assume that all the inhabitants of Sunnydorf would buy a lottery ticket together and decide to split the prize in equal shares if they win. Well, congratulations to them, because they won the prize. Now each inhabitant receives a share of $10,000 additionally to the wealth that they had at the beginning of this exercise. The question is, how would this affect the average, variance and standard deviation previously calculated? Well, you learned some rules about transformations with Carl in the theory slots, and we now just need to apply these rules. So we know that applying these calculation rules, adding a constant to an expected value, which is what we are doing here, we're just adding 10,000s to the existing wealth, in this case to the mean, increases the value by this constant. So if we would calculate the new average, as we do here, we could compare this value with the previous value that you calculated, the average value, and see that this new value is 10,000 units, in this case US dollars, higher than the one before. Similarly, if you want to apply the calculation rules, we know that the variance and the standard deviation would not be affected by just adding a constant to the values, such that the standard deviation and obviously also the variance would remain constant. Thank you very much for having attended the third exercise. I hope that now you know a little bit more about random variables and how to cope with the different rules, that you enjoyed, and hopefully see you in the fourth module. Have fun! Hello, and welcome to the fourth exercise of this online course. During the Rio Olympic Games in 2016, Simone Biles did a fantastic performance and won 5 medals, 4 of them of gold. She conducted such a fantastic performance that one of her special moves was granted her name to honor them. This is a Biles move. Well, in the Olympic Games, despite of all the fun of watching and all the Olympic spirit and nice spirit of the game, there is a lot of statistics behind. A lot of people bet on the different disciplines. A lot of people tend to see the games have some kind of probabilities of winning, of losing. And today we're going to use some information about the Olympic Games, especially about Simone Biles, this fantastic artistic gymnastic, to have our exercise today and answer some specific questions about probability. So if we go to the materials that we have here, we can assume, or we know, that Simone Biles, this gold medalist, can conduct this perfect Biles move in 95% of the competitions, meaning 95% of the times that she conducts a Biles move in a competition, she does it perfectly. We can now dive into the questions. First question asks us, consider that the statistics given about Biles in this exercise and assume that Biles conducting a perfect Biles is a Bernoulli random variable. This means that there is only success or failure. Either she does the Biles move perfect or she fails. The question now is, what's the expected value of a perfect Biles move? Well, since we are now moving, or we are considering a Bernoulli random variable, the probability of a perfect Biles move is 95% and represents the expected value of seeing a perfect Biles move. Now we can move to the second question. What's the variance and standard deviation of a perfect Biles move according to these statistics? Well, we know from the theory that you learned from Carl that the formula for the variance in a Bernoulli random, or for a Bernoulli random variable, is the probability multiplied by 1 minus the probability of success. In this case, we will take the probability of seeing a perfect Biles move, which is 0.95, and we will multiply it by 0.05 following these rules. Hence, this 0.0475 is the result of the variance. Similarly, we can apply the rule to calculate the standard deviation of this Bernoulli random variable, which is just to take the square root of the variance. If we take the square root of the variance, as we can read here, we just receive a value of 0.21794. This is the standard deviation. Now we are asked to use the probability mass function to calculate the probability that if Biles competes 35 times in the next years, she conducts at least 33 perfect Biles moves. Okay, we have the hint here that we need to use the binom_dist command in Excel. And we need to interpret this formula, because this formula yields the probability of a certain event to happen at most n times. This means less than n times. Hence, if we want to calculate the probability of seeing at least 33 perfect Biles, if Simone Biles competes 35 times, we need to calculate the probability of seeing at most 2 failed Simone Biles moves out of 35 moves. The probability of seeing a failed Simone Biles move is 0.05, meaning the difference between 1 and the probability of seeing a perfect Biles move, which was 0.95. And we need to here write true to state that the formula is not cumulative, meaning that we are looking for at most 2 failures. Well, if we conduct this calculation, we see that the probability that we see at least 33 perfect Biles, if Simone Biles competes 35 times, is of rounded 75%. Now we have the last question, which is use the same probability mass function to calculate the probability that if Biles competes again 35 times in the next years, she conducts exactly 33 perfect Biles moves. Well, now we can calculate something. The same formula, 2 failures out of 35, probability of failure 0.05, and in this case we would just write here false to say that we are looking for exactly 33 perfect Biles. This would yield a probability of 27.4, roughly. If we would like to apply the same formula but using different data, meaning using a different form, we could also use this. Look what I did here below is, instead of calculating the probability of 2 failures, I will calculate the probability of 33 successes out of 35. So we could come up here and we'll say 33 perfect Biles moves out of 35 attempts that she does, with a probability of success of 95%. Again, false to state that we're looking for the exact event, and we will get the exact same probability. Thank you very much. I hope that you enjoyed exercise 4, and see you in the next and last exercise. Have fun.
Welcome to the last module of an intuitive introduction to probability, decision making in an uncertain world. This last module covers the normal distribution, perhaps the most famous and most important probability distribution in everyday applications. However, before we can really talk about the normal distribution and the famous bell curve, we have to talk about the concept of a continuous random variable and a continuous probability distribution. And that's what this first lecture of this module is all about. Let's dive right straight in with a definition. A continuous random variable x can take on a continuum of possible values. Some people would say an uncountably infinite number of values. For example, many variables in everyday life are not discrete. They don't jump from value to value, like if you roll a fair die, 1, 2, 3, 4, 5, 6, or in a casino at a roulette table, 0, 1, 2, 3, 4, 5, and so on. Instead, they take on continuous values. Here I have some examples. A time to finish a task, or the length, if I produce an item, the length of the item, the thickness, the width. Now you may say, wait a minute, but time I count in hours, in minutes, in seconds. Yeah, but wait a minute, this is only our human limitation in measuring time. We can think then of hundreds of a seconds, thousands of a seconds, microseconds, nanoseconds. Time doesn't jump, time goes continuously. If we think of it as discrete, it's only because our limitation of measurements. So, continuous variables do exist. In addition, believe it or not, sometimes it's easier to think of a variable as being continuous than instead of having it discrete values. Stock prices are certainly discrete. We go in cents, or here in Switzerland in Rappen. Nevertheless, it's sometimes easier to model these random processes with a continuous random variable. So, continuous. That's really a tricky concept. And now I want to spend the rest of this lecture thinking, what is continuous variable? What does this really mean? So let's think of a random variable that can take on any real number between 0 and 1. And then I can ask the question, and let's start with a little in-class question. What is the probability that this random variable will take on exactly the number 0.123456789? Think about this. What is this probability? Before I give you the answer to this in-class question, I want you to have a look at the little spreadsheet that I prepared, because Excel has this beautiful random variable function, rand, that allows us to simulate the random variable on 0, 1. Let's do that. So here now I prepared a little spreadsheet for you using the random number function in Excel. Here in every version of Excel you have this beautiful function rand, parentheses open, parentheses closed. This particular function gives you a random number between 0 and 1. And so now look at these numbers. They are all different. Now what do you think is the chance I get a 0.123456789? Let me try this again. We have these random numbers. I click enter. We get 10 new numbers. Look at this. They change all the time. However, if you want to bet on a particular number, this is hopeless. If you think there's any chance 0.5, 0.55, or from the in-class quiz question, 0.123456789 shows up, it's not going to happen. Probability is 0. As a little aside, for the techies among you, here in Excel, of course, these are not truly random numbers. They are limitations to the computer. They're only so-called pseudo-random numbers. And I only get a limited number of digits here, so technically we only have finitely many numbers. However, this is meant as a representation of the true continuum. And in that sense, the probability of every number is 0, and we cannot hit any number that I give you ahead of time. So let's now wrap this idea, move back to the spreadsheet, to the slides, and continue with continuous random variables. There's really an infinite number of numbers between 0 and 1, and we cannot count them. If you think you can count them, give me the number that comes after 0. If you say, oh, it's 0.001, I say no. There's another number that comes first, 0.000001. And even there are many numbers, infinitely many, that come before that. Similarly, you can't give me the next number after 0.5, or give me the last number before 0.5. So we see this continuum doesn't allow us to give positive probabilities, because there are so many numbers that the total sum of probabilities in the end would be larger than 1. And we know that cannot be. Think back to the axioms we had way back in the beginning of the course. So, the probability of every individual number must be 0. So, or said differently, no individual number can have a positive probability. This is so key that I made a little theorem out of it here. Every continuous random variable in the universe has a property that the probability of this random variable taking on a value x is 0. So we can no longer talk about individual probabilities. That's just nonsensical. So what can we still do at this point? Let's think about another in-class question here. What is the probability that this random variable that I showed you in the Excel sheet comes up with a number between 0 and a quarter? Think about that. So, between 0 and a quarter, there are also infinitely many numbers. And if you play with the random number sheet, with those random numbers I showed you, you will notice that in 25% of all cases, you get a number between 0 and a quarter. Similarly, between a quarter and a half, 25% of the time, you fall into that interval. And a quarter of all numbers are between 0.5 and 0.75, and similarly 0.75 to 1. This looks awfully uniform. And that's the name of this particular distribution that we simulated in the Excel spreadsheet. It's a uniform distribution on the interval 0, 1. And there's nothing special on having the width of the interval a quarter. Here I show you intervals of the length of 0.1 between 0 and 0.1, 0.1 and 0.2, all the way to 0.9 and 1. They all show up with 10% probability. And there's nothing special that they're all sitting next to each other. If you think about how likely is it to get a number between 0.18 and 0.28, that probability is also 0.1. So we have a uniform distribution here, and it doesn't make sense to talk about probabilities of points, but as soon as we have a little range within our larger range, we can talk about positive probabilities. How can we represent them? And this is now the big change from discrete random variables to continuous random variables. In discrete random variables, we have single numbers and they have probabilities. We can't do that here. Here, we represent probabilities through areas underneath a curve. Let's look here at this illustration. Any number between 0 and 1 is possible. It has probability 0, but we get a number between 0 and 1. We don't get negative numbers. We don't get numbers larger than 1. Now look at this rectangle here. A square, we have the whole area is really 1. It has a width of 1. It has a height of 1. So the whole area is 1 times 1. Now, here we look at the probability between 0.18 and 0.28. This has a width of 1 and a height of, a width of 0.1 and a height of 1. So this has an area of 0.1 within the whole area of 1. So this is now 10% of the whole area. And this is how this green rectangle within the larger box represents a probability. And this is how we do it in general. As a quick aside, for those of you who remember integration from high school, there we also look at areas underneath the curve. Those are integrals. And if we look at an integral from a point A to the same point A, that integral for any function was always equal to 0. So here the representation of probabilities underneath curves corresponds to what you learned in high school about integration. That's just as an aside for those of you who know this. Now, this function that we need this to describe the curve is called a probability density function, or PDF for short. It has the following properties. This function needs to be greater or equal 0 for all elements. We cannot have negative elements. It's either equal to 0 or positive. The entire area underneath the curve has to be 1. Why? Think back to the very beginning. The basic rules of probability. The probability of the sample space, everything that's possible, always must be 1. The same thing is true here. That's now in technical terms. It means the integral of the entire area has to be equal 1. That's for the techies among you. You can just think of it that the total area under the graph of this curve is equal to 1. Now, since it doesn't make sense to talk about individual probabilities, the only probabilities we can talk about is for areas, for larger ranges, and therefore for continuous random variables. The key function is the cumulative distribution function, the CDF, typically denoted by a capital F. And that allows us to then talk about probabilities. And then I can use this function now to also calculate the probabilities for fixed ranges, the probability over an interval, as I showed you in the earlier examples. There now the probability that a continuous random variable falls between a lower number A and a larger number B is then just the difference of the cumulative distribution at B and minus the cumulative distribution at A. And so here I show you the technical calculation that goes along with this very intuitive picture. Finally, you can also draw the cumulative distribution function, which I did on this graph for you. And so the cumulative distribution function starts out at 0, moves up to 1, and then stays 1 forever. In my experience, students appreciate this function less. They prefer graphs underneath the density function. So for the remainder of this course, I will also focus on that. Areas underneath the density. So, to wrap up this very long but very important lectures, when we talk about the normal distribution, we need to get a good feel for continuity, what it means for a distribution to be continuous. Therefore, we briefly talked about continuous random variables and then looked at this most simple continuous distribution, namely the uniform on 0, 1. And the key takeaway that I need for you to understand is a representation of probabilities as areas underneath a curve. That's the key concept which we will need to calculate probabilities for some cool applications as we go forward. So, please come back for more lectures. In the next lecture, we start with the normal distribution, and then you will see continuous distributions in action. Thanks, and see you soon. Welcome back to an intuitive introduction to probability, decision making in an uncertain world. Now we are ready to learn about the normal distribution, the perhaps most famous probability distribution. Many people have seen at some point in their life the famous bell curve. Now, the first question we may have, why is this bell curve, the bell shape, so important? Because it shows up in many real-world applications. Here is sort of a technical, a mathematical explanation for that. I just want to briefly mention this. It's not really important as we move on, but let's briefly talk about the central limit theorem. This is a very cool math theorem which says the following. If you add many effects that are a little random, but have roughly the same variance, the same volatility, the same variation, then the compound process of these many little processes in the end has the normal distribution. And the amazing thing is that this very technical, very difficult Don't look at the proof. It's really nasty. It has a nasty mathematical proof. It's ugly. It's very, very difficult. Nevertheless, this very technical result is extremely relevant in everyday applications. Why? Because we have processes where lots of little things come together. If you think about markets, in particular large markets where we have many suppliers and many buyers, many sellers and many buyers, there we have lots of little opinions of what should be a price, and as a result, there we see the normal distribution in action. Similarly, in production processes, where we have lots of little things going on in the production of an item, where we have various variables from our surroundings like air pressure, temperature, and so on, they compound to something that's often very well approximated by the normal distribution. Then, other important applications are in the field of statistics, when we there talk about the probability distributions of sample means or sample proportions. Guess what? The normal distribution shows up as the samples get large. In business, there's in the area of operations management something called quality management, the so-called Six Sigma, and there the normal distribution is used. In finance, people have a very important risk concept of value at risk. There, the normal distribution has been used a lot. Recently, it has been criticized there, and for some various reasons. Nevertheless, probability distributions close or similar to the normal distributions are used there to this day. So, now the normal distribution, this bell curve. The bell curve is an example of a density function that we saw in the previous lecture. This particular density function is bell-shaped. It's symmetric around the mean, which is exactly in the middle, and the spread is determined by the standard deviation sigma. This distribution only depends on two parameters: the mean, which is given by the mu, and the standard deviation given by a number sigma. If you and I agree on mu and sigma, we indeed have the same normal distribution. Here, just to scare the living daylights out of you, I show you the density function. It has a number pi, the famous geometry constant 3.14 in it, and the Euler number 2.71828, and infinitely many more digits, named after the Swiss-Russian mathematician Euler. And again, here you see the picture. Now, let's look at this graph. What happens to the distribution, to the bell shape, if we change mu or sigma? If you first look at the red, green, and blue graph here, they all have the same mu. That means they are all centered at the same number. They all have the peak, the maximum, at the same number. They distinguish themselves with the level of sigma. Notice, the larger sigma gets, the larger the standard deviation, the larger the spread. That means the curve, the maximum, goes down and the curve goes wider out. Now, the last curve, the purple one, has a smaller mu. That means it moves to the left. It's now centered at a smaller value. So, the key idea: mu gives us a point where it's centered. A smaller mu moves the curve to my left. A larger mu moves the curve to my right. Sigma, the smaller sigma, the more narrow the curve gets and the higher it is. Again, the key concept from the previous lectures. The bell curve itself doesn't give us probabilities. It's the areas underneath the bell curve. Those are the probabilities that we need. And remember, we can calculate those with the cumulative distribution function. Because it's so important, let me repeat it one more time. For continuous distributions, such as the normal distribution, probabilities are areas underneath the curve, and we calculate those with the cumulative distribution function. Now we have a problem. There is no closed form formula. There is no simple formula for the cumulative distribution function capital F of the normal distribution. We can only approximate these areas. In the old days, before we had modern computers and cool software, people had to do table lookups. Some people, either by hand or with supercomputers at the time, calculated these tables and they were printed in probability books. Sadly, nowadays, still some people think that's the way to go. No, it's not. It's very old-fashioned. It's so the last millennium. So my advice, rip out those pages out of your probability textbook and roast marshmallows on them. They are useless. Nowadays, we want to use software packages. If you use some fancy mathematical software packages, it does have the normal distribution. But you don't need even that. Excel can help you to calculate any normal probability that you may care about. And that's what we do here. The function we're going to use is a norm.dist function in Excel. Here it's written down. It has 4 arguments that we need to enter. Let me show you right away an example of this function in action. Here we have a normal distribution with a mean of 63, a standard deviation of 5. And I want to know what's the probability that this random variable takes on a value less than 65 or larger than 65. What do I need to type in? Norm.dist. The value I care about right now is x65. Second number is a mean, 63 in this case. The third number is a standard deviation, sigma 5. And finally, the last entry is true or 1. Remember back to the binomial distribution, true or 1 always means we're working with the cumulative distribution function. And that's the only thing that makes sense here. So don't even think about it, just type in true. And we see, there it goes. 0.6554 is the probability that this random variable will take on a value of less than 65. Using the complement rule, 1 minus this probability gives us a probability of the right tail, 0.3446. So you see, we don't need complicated tables and look for numbers in a complicated table. We just type a one-line command in Excel and we get the probability we care about. So, let me wrap up this lecture. We talked about the famous bell curve, which is the density function or the graph of the density function of the normal distribution. And calculations of those probabilities from the normal distribution is really easy. We can just use the norm.dist function in Excel. And UXL does have that function. So, in the next lecture, we now look at examples and start having fun with this function and calculate normal probabilities. So, please come back for more fun with the normal distribution. Thank you. Welcome to the third lecture on our module on the normal distribution. So, let's now calculate some normal probabilities. Here is an example that I got from a student a few years ago. He worked for a technical consulting company in Florida. And one of their clients was a company that he didn't name, so I called it Florida Elevated Roadways, Ferry. This company, Ferry, makes or builds pillars and elevated roadways in Florida. Why do they have to do this? Florida has a lot of swamp, so you can't put a street on the ground in many areas, the way we do it here in Switzerland. Instead, you have to put a solid foundation into the swamp, put up a pillar, and then put the road on top. The construction of these pillars, of course, is key to make this safe, a safe road. So, after a pillar is constructed, it is measured and tested in various ways. One particular parameter let's call it just x here, is the following. What you're worried about is that this pillar may sink into the swamp. So what companies then do, they put a lot of pressure on the foundation of the pillar, push it into the ground, and then take the pressure away and see whether the pillar has actually sunk or whether it stood up to the pressure. Here is a related picture I got from a student in Switzerland. You see, they put a lot of pressure on this pillar here in the middle. And this is a key test, a key stress test for the pillar. Of course, it's important for me that the pillar can hold up the street, because I don't want to drive on the street and suddenly there's no pillar and bam, and then I become alligator food. I don't want that to happen. So this is a key test. Now, these pillars are allowed to sink a little bit, but not too much. Now, let's abstract from the units here. Our variable x that describes this particular physical feature has an average value of 0.8. But it doesn't always reach exactly the average. It varies. Think about this. These are pillars put into swampy ground, perhaps in 100 or 110 degree Fahrenheit weather. There are mosquitoes. There's lots of uncertainty in the construction of these pillars. As a result, the physical goal of a 0.8 isn't always reached. There's variation. Here, the student told me, let's assume the variation is about 0.1. So, in our language, the standard deviation is 0.1. Now, the pillar is classified as a failure if the actual value that x takes on is 1 or larger. Then the pillar is not considered safe. So now the question is, how likely is it that there is a failure in the pillar? That's important. Maybe there may be lawsuits, I may have extra construction costs, all kinds of trouble may result. Now, the student said that when they calculate such probabilities, they use the normal distribution, because I've had good experience with that distribution. So, what is the probability that a pillar will fail under these assumptions? We can use the norm.dist function. You find it in the same menu in Excel where we found the binorm dist function. So here we have norm.dist. The critical cutoff value is the number 1. Our mean is 0.8. The standard deviation 0.1. And again the word true. And we see, if you type that into Excel, you get the answer 0.97725. But remember, norm.dist is a cumulative distribution. It gives us, by definition, the area to the left of the cutoff value 1. But we care about the area to the right, numbers above 1, because that's a failure. So we use once again the complement rule, 1 minus the probability we just calculated, and the final answer is the probability of a pillar failure is about 2.3%. That's of course rather large if you build hundreds and hundreds of pillars. So you actually want to improve the process relative to the numbers I gave you. Okay, let's move on. Here I randomly calculated some other probabilities. Look at this. The second example, I have a mean of 1, a standard deviation of 5, and I picked the number 11 as a probability. And 3 more randomly chosen examples. And look at this. The probability is always the same. What the heck is going on here? What do these 5 calculations have in common? Can you see it? The answer is they have one thing in common. The difference between x and the mean divided by the standard deviation is always the same number, in this case 2. And that's the key reason why they all get the same probability. And so this is a key takeaway. The actual number x, mu, and sigma do not matter. The key figure that matters is this ratio, x minus mu divided by sigma. That's really what determines the probability. By the way, there was nothing special about that ratio being 2. Here, the ratio is -1. again, all 5 probabilities are the same. And this is actually now a key property that all normal distributions have, and it leads us to the so-called standardized normal distribution. We can actually transform any normal distribution with any mean mu and any standard deviation sigma into the so-called standard normal distribution, which has a mean 0 and the standard deviation 1. Any one of you who has heard the concept of a z-score or a z-value or z-value has worked with standard normally distributed random variables. The nice thing is, there's a special function for this in Excel, which is norm.s.dist, S for standard normal. Here now, I have to warn you. In the very latest version of Excel that I'm using here, this function has 2 arguments, the z and the true. If you have an older version of Excel, 2011 or earlier, there is no true. It's just z. But otherwise, it's all the same. And so here now, instead of using the norm.dist on the original values, you could also first calculate z and then use the norm.s.z. You will get the same answer. No big deal. Here's a nice illustration. You see on the right is the origin is a standard normal distribution. On the left is the original distribution. And you see on the original distribution with a mean of 0.8 and a standard deviation of 0.1, the probability to the left of x equal 1 is the same as in the standard normal to the left of z equal 2. And I can use the standard normal distribution for any value of z. Again, nothing special about z equal 2. Here's other numbers for z equal -1. To sum up, we saw a first cool application of the normal distribution from engineering. Then we learned about the standard normal distribution and the function norm.s.dist in Excel that allows us to calculate the standard normal probabilities. So in the next lecture we will learn about more calculations we can do. Please come back for those. Thank you. Welcome back to an intuitive introduction to probability, decision making in an uncertain world. In the last lecture, we started playing around with the norm.dist and the norm.s.dist function in Excel to calculate some normal probabilities. Let's continue with this and step by step solve more and more difficult problems. Here's now next question we may ask. What is the probability that we get an x in a range of variables? So here, what's the probability that an x shows up in this yellow range between a and b? So I want this area underneath the curve. So back to Ferry. Remember our construction company in Florida? And now here's a new question. What is the probability that this physical parameter x ends up at a particular pillar between 0.7 and 1. So I no longer want the probability just below 1. No, I want the probability in the range between 0.7 and 1. Easy now, because we can handle the norm.dist function. The probability that x falls between 0.7 and 1 is the difference of the cumulative probabilities. So I do the cumulative probability at 1 minus the cumulative probability at 0.7. I use these two norm.dist commands and voila, about 82%, or to be more precise, 81.86%. So the area underneath the curve between 0.7 and 1 of our normal distribution that we're using here for Ferry, that area is 81.86%. Remember the standard normal. I could now transform the 0.7 into a -1 z value, the 1 into a 2 z value, and then use the norm.s.dist function. And that's what I've done here. Same answer, of course. I don't need to do this, but I could go this detour via the standard normal. Now, many people, if they remember something from the normal distribution, then it's this plus minus 1 sigma plus minus 2 sigma and so on probability. This is what we see here. Every normal distribution has these properties. The area underneath the curve around the mean, between mean minus 1 standard deviation and mean plus 1 standard deviation, is 68.27%. Plus minus 2 standard deviations is 95.45%. Plus minus 3 standard deviation is 99.73%. Every normal distribution has these properties. Finally, there's one last calculation we need to learn about, which is the inverse calculation. Let's start with the following question. Theory doesn't like a 2.3% failure probability. That's way too high. Let's now say they want a failure probability of only 0.1%. Put differently, they want a 99.9% probability of producing a good pillar. Where would this cutoff X have to be? If they could decide on this cutoff X between good pillar and bad pillar, where should that be? Notice now, this question is different than the previous questions. Previously, 1 or 2 values for X were given, and we had to calculate a probability. Now, we want to go the other way around. Probabilities have been specified. 0.999 good, 0.1% bad. And now we want to go back and find an X that goes with these probabilities. So, down here, we want the norm dist of this unknown number for our distribution with mean 0.8 and standard deviation 0.1 to be equal to 0.999. Now, I know some Excel wizards would say, oh, there's a goal-seek function or a solver function that I could use here. Yes, but it's way more elegant to do it using the norm.inf function. How cool is that? Excel gives us a function, norm.inv, inv for inverse, that gives us this value x when we specify the probability. So, if we type in norm.inv of this probability p, and of course I have to give Excel the mean mu and the standard deviation sigma, then it spits out the value xp, so that to the left of xp I have the probability p, and to the right of xp I have the probability 1 minus p. Maybe some of you have heard the name percentile or quantile of a distribution. That's exactly what we're computing here. So, here's an illustration. I always think of, I have a probability p that I put in the left tail of the distribution. I put that probability p in, and at some point I run out of probability. At that point, I get the value xp. In the theory example, I would now type in norm.inv of 0.999, the mean 0.8, sigma 0.1, and voila, I get the number 1.109. Now, what does it mean? In our application, this has the following interpretation. If the cutoff is at 1.109, then there's 99.9% probability to the left. In theory, that means there's a 99.9% chance of a pillar having an x less than 1.109, of being now, under this new regulation, being a good pillar. And there's only a 0.1% chance of being above this cutoff. We can check this and we get the number using norm dist. I can now go back and check. There's a tiny rounding error here, but other than that, with respect to 3 digits, I get exactly my 0.999. Here's a summary of all the Excel functions that we may need. There's a norm dist function and the norm sdist function we saw in the previous lecture. There's a norm inf inverse function that we saw in this lecture. Actually, there's also an inverse for the standard normal, and those are the 4 functions that we can use in Excel. And with those 4 functions, I can calculate any probability or any inverse value that I want. And in the last lecture of this module, I will show you another cool application with these functions in action. This wraps up this lecture. We learned more about calculations with the normal distribution. Most importantly, we learned the inverse of the normal distribution and the corresponding function in Excel. Thanks for your attention. Please come back for more. In this last lecture in our module on the normal distribution, I want to show you one more nice application that I learned about a few years ago from a student. This student works for a manufacturing company that uses a lot of zinc. Zinc is a metal that doesn't rust, and so it's used to cover iron or other metals which may rust. And so for this company, this was very important. They had to buy a lot of zinc, and as a result, the bottom line of this company was very sensitive to the price of zinc on the world market. The company had developed a forecasting model and for the price of zinc 1 month in the future. And the student told us that they used the normal distribution to forecast the price. Now, based on historical prices and recent price changes, they always estimated a mean for the distribution, an expected price, mu, and a volatility, a standard deviation, sigma. I recently looked up the current prices and volatilities and rounded them to the numbers here on this slide. So let's now work with a model for the price of zinc 1 month from today, with an average of $2,250 per metric ton, with a standard deviation of $110 per metric ton. Here's the first question we may ask. What is the probability that the price 1 month from today is exactly $2,288.12? What's the answer? Of course, it's 0. We are using the normal model here. Remember, with a continuous probability distribution, such as the normal distribution, the probability on any given number is 0. So this question doesn't make sense. Let me start with a more reasonable question. And let's make this an in-class quiz question. So you can go to Excel and try to answer this question. What is the probability that the spot market price 1 month from now exceeds $2,300 per metric ton? So please open up your Excel, type in the right norm dist formula and give me the answer. Here's my answer to the question of the price exceeding $2,300. If you type in norm.dist of 2,300, the mean 2,250, the standard deviation 110, don't forget the word true at the end, you obtain a probability of about 67.5%. But keep in mind, norm dist always gives us the probability in the left tail of less than or equal to the x number, in this case 2,300. The question, however, asks the probability of exceeding 2,300. Exceed means larger than 2,300. So once again, we need to use the complement rule, 1 minus that probability, and so we obtain a probability of about 32.5%. I hope you had some fun with this question, because here's already the next question for you. What is the probability that the spot market price falls between 2,200 and 2,400? Put differently, what's the probability that the spot market price of zinc 1 month from today falls into this range? Go back to Excel and answer the question. Here's my answer. I need two norm dist calculations now. Remember the probability for a range. We always calculate the cumulative probability for the upper number and then subtract the cumulative probability for the lower bound. In this case, we use norm dist for 2400 minus the norm dist for 2200 and all the other garbage that we need to plug in. The answer is about 59%. Let's go straight to the third question. There's a 90% probability that 1 month from now the price of zinc falls below what level? So I now care about the cutoff between the bottom 90% of possible prices and the top 10% of possible spot market prices. What is your answer? Here's my answer now to this in-class question. Of course, now I had given you the probability of 90% and asked you for an x. Remember, that's now the inverse function. So I need to type in norm.inv for inverse. The probability is 0.9. I put in mean and standard deviation and I obtain the answer of $2,390.97. So the interpretation is there's a 90% probability that we fall below this price and there's only a 10% chance that the zinc price will be above $2,390.97. And as a last question, here's a little tricky question. I want a 90% interval that's symmetric around the mean. So give me a 90% range symmetric around the mean that the price is in this range. What's your answer on that? Think about it. So this was a little tricky. Since I want 90% in the middle, that leaves 10%, 5% in each tail. So the 90% interval around the mean has the upper cutoff at 95 and the lower cutoff at 5. In that way, it's symmetric around the mean and it leaves 5% in each tail. So to answer this question, you have to use norm INV twice. Once with the probability of 0.95 and a second time with the probability of 0.05. If you do the calculation, you get the answer. With 90% probability, the price will fall between the lower bound of $2,069 per metric ton and the upper bound of $2,430 per metric ton. This finishes our final application of the normal distribution and we did a whole bunch of calculations in Excel. Sadly, this ends our MOOC on an intuitive introduction to probability, decision making in an uncertain world. I had a lot of fun teaching this class, putting together this material. I also hope that you had some fun and that you learned something along the way. We are looking forward to your feedback to our class and hope we got you excited about probability and that you no longer say, I hate probability, but that you actually say probability is fun and useful and I want to learn more. Thank you very, very much.
Welcome to the fifth and last exercise of this online course. Today we are going to help the Dean of the fictive University of Claudidorf to see if the students of his classes are cheating or not. His assumption is that if the grades of the students in a subject are normally distributed, then students are not cheating. However, if the grades are somehow not normally distributed, something strange is happening and he will take a closer look at it. In order to do this, we will have a look at the grades of 2 different subjects at this university and after answering some easy questions, plot a QQ plot to find if the data in the 2 different subjects are normally distributed. For this, we have summarized here some data. In the first table that we see here, we have the grades, which go from 1 to 10, and then the frequency of the grades in 2 subjects. The first subject is Introduction to Analysis. We see 0 students have a 1, 3 students have a 2, other 3 students have a grade of 3, and so forth and so on. Additionally, we have the frequency of the grades in Introduction to Probability. So we would have 8 students with an 8, 5 students with a grade of 9, and so forth and so on. Additionally, here we have a student rank and the grades ordered by this rank. So 1 would correspond to the student with the poorest grade, and if we go further down, 29 would correspond to the student with the highest grade. So we have here the grades in each of the subjects ordered by a ranking. Now, taking this information, we can go and answer the questions. The first question asks us to plot a histogram of the grades in every subject. Additionally, we get here a hint which asks us to use the command insert, graph, and column graph to plot this histogram. So what we need to do is to select the column of data of each of the subjects that I just show, click on insert, graph, column to plot a histogram. So here, answer to this question. Here we see the histogram of the frequency of the grades in the subject Introduction to Analysis. Although we don't know much about the data, we see that this distribution somehow could resemble a normal distribution. If we scroll a little bit down, here we have the histogram for the frequency of the grades in Introduction to Probability. Again, although we don't know much about the data yet, we see that this structure is far away of what we would expect in a normal distribution. Now we are asked to interpret these 2 graphs, and specifically we are asked to conduct some iconometrics and see what we can tell about the 2 distributions. Well, as I just mentioned, the distribution of the grades in the course Introduction to Probability does not look normally distributed and instead looks a little bit shifted to the right. However, the distribution of the grades in Introduction to Analysis tend to resemble a little more the structure of a normally distributed graph. Now we are asked the core question of this exercise, which is to create a QQ plot for the grades for both subjects, by which we will be able to evaluate if the data are indeed normally distributed. The instructions are as follows. First, we need to sort the grades in ascending order. Well, if you look at the data specifically, I already did that for you, so you have them already in your Excel file. Secondly, we need to create a column for each grade that shows the rank proportion. This means the percentiles. Don't worry, I will show you now how to do this. Then the percentile of this candidate, or each candidate is its rank minus 0.5. We need to do this in order to have a centered percentile and not the percentile of the above category. Don't worry again, I will show you how to do it specifically. Using these percentiles, we will calculate the corresponding z-score, and then we will just need to plot the z-score against the grades of each of the students in each of the subjects. So, as promised, here I will show you how to calculate the percentiles, the z-scores, and how to plot them. So here we have the student's rank, which is exactly the same that you saw at the very beginning. Now we need to calculate the percentile. Well, the percentile is calculated by just taking the grade of the first student, the smallest grade of the students, subtract 0.5 because we want to have the percentile of the centered student, and divide it by 29, which is the total number of students. This will give us, or a way to interpret this, is to see that the student in rank or in position 7 will be better than 22.4% of the students. If we scroll down a little bit, student 16 will be better than 53% of the other students. We can do this for the rank, and then we need to transform this rank to the z-score in order to be able to plot the QQ plot. We can easily do this by applying the formula norm.s.inf of the percentile. If we just scroll down, we will get the z-score for every of the percentiles for every student's rank. Then the last step that we need to do is to plot the grades, the actual grades in each subject of each student, obviously ordered by this ascending ranking, against the z-score. And additionally plot the z-score against the z-score in order to have a straight line in our plot. If we just plot the values that we just calculated, this is what we receive, which is our desired QQ plot. Here we see that the blue dots, which are the grades in analysis, are much closer to the gray dots, which represent this straight line, which would represent a perfectly normally distributed data, and are therefore closer to a normal distribution. However, the grades in probability have a clear different shape than a straight line, the straight line that we would have here with the gray dots marked by the z-score, and therefore the dean of the University of Claudidorf could assume that if somebody is cheating, then it's probably somebody in the course of probability. Thank you very much. I hope that you really enjoyed the course and learned a little bit more about statistics. I definitely enjoyed creating these exercises for you and recording them for you. Hopefully see you soon in another online course. Thank you very much, and of course, have fun.